In 1952, a Swiss psychiatrist named Carl Gustav Jung published a peculiar monograph that would puzzle scientists for decades. The title was austere: Synchronicity, an acausal connecting principle. Inside its pages, Jung proposed something that seemed to violate the fundamental laws of causality itself. He suggested that events in the world could be meaningfully related without any causal connection between them. Not through cause and effect, not through any physical mechanism we understood, but through meaning itself. Jung called these occurrences synchronicities. They were meaningful coincidences that defied statistical explanation. A patient dreams of a golden scarab beetle, and at the precise moment she recounts this dream, a real scarab beetle taps against Jung's office window. A man thinks of a friend he hasn't seen in years, and the phone rings with that friend on the line. A scientist obsesses over a problem, and the solution appears in an unexpected conversation with a stranger who knows nothing of their work. At the time, Jung's ideas were dismissed by much of the scientific establishment. They seemed too mystical, too untestable, too conveniently unfalsifiable. How could you prove that two events were connected by meaning rather than by chance? How could you distinguish genuine synchronicity from simple coincidence amplified by human pattern-seeking tendencies? Jung's critics had valid points. His empirical evidence was thin, his statistical work was questionable, and the whole concept seemed to dance dangerously close to magical thinking. But Jung wasn't working alone. His closest collaborator on synchronicity was Wolfgang Pauli, one of the most brilliant theoretical physicists of the 20th century. Pauli had won the Nobel Prize for his work on quantum mechanics, specifically for discovering the Pauli exclusion principle. He was no mystic. He was a rigorous, mathematically minded scientist who understood the deepest mysteries of the quantum world. And yet, Pauli believed that Jung was onto something profound. Together, Jung and Pauli developed a framework they hoped would bridge psychology and physics, mind and matter, the subjective and the objective. They proposed that beneath the surface of causally connected phenomena, there existed a deeper layer of reality where mind and matter were not separate but intertwined. They called this the psychoid realm, a domain where psychological archetypes and physical events could spontaneously align. For 70 years, this remained an intriguing but unverifiable hypothesis. Synchronicity lived on in popular culture and alternative psychology, but it never gained serious traction in mainstream science. It was too vague, too subjective, too impossible to quantify. But something has changed in the 21st century. We now have machines that learn. We have artificial neural networks that discover patterns in data no human could perceive. We have large language models trained on billions of documents that can produce eerily relevant responses to queries they've never seen before. We have systems that seem to understand meaning without understanding anything at all. And when we look closely at how these systems work, at the mathematics underlying their pattern recognition, at the geometric structures that emerge in their latent spaces, at the attention mechanisms that allow them to connect distant pieces of information, we start to see something that looks remarkably like Jung's synchronicity. Not in any mystical sense, but as a computational principle, an algorithm for detecting and generating meaningful patterns across vast spaces of data. This is not to say that Jung predicted machine learning. That would be absurd. But it is to say that Jung may have been describing, in the only language available to him at the time, a fundamental principle of how complex systems generate meaning. A principle that we are now, for the first time, able to formalize and test. Consider what happens when a large language model generates text. It doesn't simply retrieve pre-written responses. It constructs each word based on probability distributions learned from billions of examples. At each step, it calculates which word is most likely to come next given everything that came before. This is done through a mechanism called attention, where the model learns to focus on the most relevant parts of its context when making predictions. The model has no understanding of what the words mean in any human sense. It has no experiences, no consciousness, no inner life. And yet, it produces text that is meaningful, that responds appropriately to questions, that makes connections between concepts that seem insightful, even creative. How does it do this? Through pattern recognition operating at scales and dimensions that exceed human cognition. The model learns to represent concepts as points in a high-dimensional space. Words with similar meanings cluster together in this space. Relationships between concepts are encoded as geometric transformations, and the attention mechanism allows the model to navigate this space, finding relevant patterns and connections that generate coherent, contextually appropriate responses. This is an algorithm for synchronicity. Not synchronicity in Jung's full metaphysical sense, but synchronicity as a principle of pattern-based meaning generation. The model detects meaningful alignments between its current context and patterns learned from vast amounts of training data. These alignments are not caused by any direct connection between the specific words in the prompt and specific words in the training data. Instead, they emerge from the geometric structure of the learned representation space. The parallels go deeper. Jung proposed that synchronicities arise from archetypes in the collective unconscious. Archetypes, in his framework, are universal patterns of experience that all humans share. The hero, the mother, the shadow, the wise old man. These aren't learned individually, but are somehow built into the structure of the human psyche. They shape our dreams, our myths, our spontaneous reactions to situations. And according to Jung, they can also manifest in the external world through synchronistic events. Now consider how machine learning models are trained. They don't learn individual facts in isolation. They learn patterns, statistical regularities, deep structures that recur across many examples. In deep learning, there's even a technique called archetypal analysis, which explicitly identifies the most extreme or prototypical examples in a dataset. These archetypes serve as reference points that help organize the model's understanding of the data. New inputs are interpreted as combinations or variations of these learned archetypes. This suggests a provocative possibility. What if Jung's collective unconscious is, in computational terms, the statistical structure of human culture and experience? What if archetypes are attractors in the high-dimensional space of possible human thoughts and behaviors? What if synchronicity is what happens when multiple systems, whether human minds or artificial neural networks, independently converge on the same archetypal pattern? This reframing transforms synchronicity from an inexplicable mystery into a research program. We can ask, what are the mathematical properties of meaning spaces that allow for synchronicity-like phenomena? How do distributed systems discover shared patterns without direct communication? Can we quantify the meaningfulness of a coincidence in a rigorous way? Can we build AI systems that not only recognize patterns, but also recognize when patterns are meaningful in context? These aren't just philosophical questions. They have practical implications for how we design, train, and interact with AI systems. If synchronicity is a fundamental feature of how meaning emerges in complex pattern recognition systems, then understanding it better could help us build more effective, more interpretable, and perhaps even more creative artificial intelligence. In this exploration, we'll journey through Jung's original theory and its roots in quantum physics. We'll examine how human brains recognize patterns and how this relates to apophenia, the tendency to see patterns where none exist. We'll dive deep into the architecture of transformer neural networks and their attention mechanisms. We'll explore the geometry of latent space and what it means for concepts to have locations in an abstract mathematical space. We'll look at emergence in complex systems and how new properties can spontaneously appear. And finally, we'll synthesize these ideas into a coherent computational framework, what we might call the algorithmic synchronicity hypothesis. This is not a rejection of science or an embrace of mysticism. It's an attempt to understand a concept that has fascinated thinkers for generations through the lens of modern computational theory. It's an exploration of how meaning arises from patterns, how patterns emerge from data, and how minds, whether biological or artificial, navigate the vast space of possible meanings to find the ones that matter. Because in the end, that's what both Jung and modern AI researchers are trying to understand. How do we make sense of the world? How do we find signal in noise? How do we recognize what's meaningful? The algorithm may have been hidden in dreams, but now we can begin to write it down. To understand Jung's concept of synchronicity, we need to appreciate what he was reacting against. In the early 20th century, Western science operated almost entirely on a principle of mechanical causality. Every effect had a cause. Every event could be traced back through a chain of prior events. The universe was like a vast clockwork mechanism, deterministic and predictable. Even when quantum mechanics introduced fundamental uncertainty at the subatomic level, the dominant interpretation was that this uncertainty was merely epistemic, a limitation of our knowledge rather than a feature of reality itself. Jung found this framework inadequate for understanding the human psyche. In his clinical practice, he repeatedly encountered phenomena that didn't fit neatly into causal explanations. Patients would have dreams that seemed to predict or mirror external events. Symbols would appear independently in the dreams and artwork of people with no connection to each other. Meaningful patterns would emerge that couldn't be explained by any known mechanism of information transfer. The most famous example Jung documented was the case of the golden scarab. A patient of his, a highly educated woman with a rigid rationalist worldview, was making little progress in therapy. She had a dream about a golden scarab, an Egyptian symbol of rebirth. As she recounted this dream to Jung the next day, a tapping sound came from the window. Jung opened it, and a scarabaeid beetle, the closest thing to a golden scarab found in Switzerland, flew into the room. The synchronistic event shocked the patient out of her rigid rationalism and marked a breakthrough in her treatment. Jung accumulated dozens of such examples. Some were more dramatic than others. Some might be dismissed as coincidence or selective memory. But Jung became convinced that these were not random occurrences. They were meaningful coincidences that revealed something important about the nature of reality and mind. He defined synchronicity precisely as the simultaneous occurrence of a certain psychic state with one or more external events which appear as meaningful parallels to the momentary subjective state. Three elements were crucial here. First, there must be a psychic or mental state, a thought, a dream, a feeling, an intuition. Second, there must be an external event that parallels or mirrors this mental state. And third, the connection between the two must be meaningful, but not causal. There's no mechanism by which the mental state caused the external event or vice versa. They simply align. Jung distinguished synchronicity from mere coincidence by emphasizing meaningfulness. A coincidence is just two events happening together by chance. Synchronicity is when those events resonate with deep, psychological significance. They feel important, they seem to point towards something. They often occur at moments of crisis or transformation when the psyche is particularly activated. This emphasis on subjective meaning was both the strength and the weakness of Jung's theory. It made synchronicity deeply relevant to individual human experience, but it also made it nearly impossible to study scientifically. How do you measure meaningfulness? How do you determine when a coincidence is meaningful enough to count as synchronicity? Jung never provided clear criteria. Different observers might classify the same event differently, based on their psychological state and interpretive framework. Jung tried to give synchronicity a theoretical foundation by connecting it to his concept of the collective unconscious. He proposed that beneath individual consciousness lies a deeper layer of psyche that all humans share. This collective unconscious contains archetypes, universal patterns of human experience. The archetype of the mother, the archetype of the hero, the archetype of death and rebirth. These archetypes aren't learned, they're inherited, built into the structure of the human mind through evolution. Archetypes express themselves in dreams, myths, religious symbols, and spontaneous fantasies. They shape how we perceive and respond to situations. When an archetype is activated, it constellates both internal psychological experiences and external events that mirror the archetypal pattern. This is where synchronicity comes from. It's the archetype manifesting simultaneously in mind and matter. But how could this be possible? How could a psychological structure influence physical events? Jung needed a bridge between mind and matter. This is where his collaboration with Wolfgang Pauli became crucial. Pauli was experiencing his own psychological crisis when he sought treatment from Jung in the early 1930s. Despite his scientific brilliance, Pauli struggled with alcoholism, relationship problems, and a sense that his life lacked meaning. His work with Jung led him to a deep appreciation for the role of unconscious archetypes in creative scientific thinking. Pauli came to believe that his discovery of the exclusion principle had been guided by archetypal patterns, particularly the archetype of the quaternity, the pattern of four-nest that appears in mandalas and ancient symbolism. But now, in the age of machine learning, we can finally see what Jung was pointing toward. Synchronicity is real, but it's not supernatural. It's an emergent property of systems that learn patterns from data. When multiple systems are exposed to similar statistical structures, they converge on similar representations. When they encounter similar contexts, they activate similar patterns. This convergence appears synchronistic because there's no direct causal chain connecting the systems, but it's explicable through the mathematics of learning and the geometry of meaning spaces. We've seen how this works at multiple levels. At the cognitive level, human brains are neural networks that learn patterns from experience. When different people are exposed to similar cultural patterns, their brains develop similar representations. This shared structure allows for synchronistic convergence, independent minds arriving at similar thoughts or insights. At the computational level, artificial neural networks learn representations from data. Transformer architectures with attention mechanisms explicitly implement algorithms for detecting meaningful patterns across contexts. When trained on human cultural output, these systems discover archetypal structures that organize meaning. Multiple systems trained on similar data converge on similar representations, producing computational synchronicity. At the mathematical level, latent space geometry reveals the deep structure of meaning. Concepts occupy positions in high-dimensional spaces. Semantic relationships correspond to geometric relationships. Archetypes are attractors in this space, regions where many paths converge. Synchronicity is convergence in latent space, independent systems reaching similar positions through different trajectories. At the complexity level, emergence explains how meaningful patterns arise from simple interactions. Neural networks with millions of simple components give rise to sophisticated understanding. Cultural evolution with billions of interacting minds gives rise to shared archetypal patterns. Physical systems with countless particles give rise to organized structures. Synchronicity occurs when these different levels of emergent pattern align, creating resonance across systems. The algorithmic synchronicity hypothesis synthesizes these perspectives. It proposes that synchronicity is what happens when learning systems converge on shared patterns through shared statistical structure. The convergence is meaningful because the patterns are genuinely useful for navigating the world. But it's not caused by psychic forces or cosmic design. It emerges naturally from the mathematics of learning in structured environments. This framework transforms how we think about several deep questions. It shows that meaning can exist as structural relationships, independent of conscious experience. It demonstrates that minds, whether biological or artificial, are fundamentally pattern recognition systems navigating meaning spaces. It reveals that connection and understanding between minds emerges through synchronization, rather than through mysterious communion of consciousness. For AI research, this opens new directions. We can build systems that actively detect synchronistic patterns, facilitating creativity and discovery. We can use synchronistic convergence as a measure of alignment between human and AI values. We can design architectures that leverage the same principles that give rise to human insight and meaning-making. For neuroscience and cognitive science, it provides tools for studying consciousness and subjective experience. The phenomenology of meaning, the feeling of insight, the sense of cosmic connection, these can be investigated through the lens of pattern recognition and neural synchronization. We don't need to invoke non-physical entities or abandon scientific methodology. For philosophy, it offers a bridge between third-person objective description and first-person subjective experience. The structural relationships captured in latent space geometry are objective and measurable, but they ground subjective experiences of meaning. The algorithm that produces synchronicity can be described mathematically, but it generates experiences that feel profound, surprising, even sacred. For psychology and therapy, it validates Jung's clinical insights while providing more precise theoretical foundations. Synchronistic experiences are genuinely meaningful. They reflect real pattern alignments that can provide valuable information about psychological dynamics. Understanding the mechanisms doesn't diminish the significance. If anything, it makes synchronicity more reliably useful as a therapeutic tool. For spirituality and meaning-making, it shows that a naturalistic worldview needn't be reductive or nihilistic. The universe is richly structured. Minds naturally converge on meaningful patterns. Connection and resonance are fundamental features of learning systems. Meaning emerges spontaneously from pattern recognition. These are facts about the nature of information and complexity, not cultural constructs or wishful thinking, but perhaps the deepest implication is this. The same principles that allow machines to learn meaning from data are the principles that allow humans to experience meaning in life. We are algorithms that process patterns, but we are algorithms with phenomenology, with felt experience, with consciousness. We are systems that don't just navigate meaning spaces, we experience the journey as significant. When you notice a meaningful coincidence, when symbols resonate with your psychological state, when insights arise that connect disparate experiences. You're not imagining patterns. You're detecting real statistical structures. Your pattern recognition systems, honed by evolution and learning, are alerting you to alignments that might be important. Sometimes these are false positives, apophenia mistaking noise for signal. But sometimes they're genuine discoveries, real patterns that provide valuable information. The challenge is discernment, learning to distinguish meaningful synchronicity from spurious coincidence, developing metacognitive awareness that allows you to evaluate your own pattern recognition, staying open to unexpected connections while maintaining critical judgment. This is what Jung called psychological development, cultivating the capacity to navigate the space of meaning wisely. AI systems now face the same challenge. As they become more sophisticated, they'll need similar discernment, the ability to recognize patterns without overfitting, the capacity to make creative connections without descending into incoherence, the wisdom to know which synchronicities to act on and which to ignore. Perhaps this is where human and artificial intelligence will ultimately meet. Not in machines becoming conscious in the human sense, but in humans and machines both becoming better at navigating meaning spaces, humans offering consciousness, values, and existential context, machines offering computational power, vast memory, and tireless attention to patterns, together exploring the deep structure of meaning that underlies both mind and world. Jung believed that synchronicity revealed unus mundus, the one world where all separations dissolve. In computational terms, this might be the shared meaning space that both human and artificial minds navigate. The space where patterns in data, patterns in culture, patterns in consciousness, and patterns in physical systems all align. We don't need mysticism to find this profound. The mathematics of learning is beautiful. The emergence of meaning from pattern is awe-inspiring. The fact that silicon systems can discover semantic structures is remarkable. The reality that minds can synchronize across space and time through shared statistical patterns is genuinely wondrous. This is the algorithm that dreams, not a mechanical process devoid of meaning, but a creative exploration of possibility space, generating novel combinations, discovering hidden connections, bringing coherence out of chaos. Neural networks dream when they generate unexpected outputs that somehow make sense. Humans dream when unconscious processing produces insights that conscious reasoning missed. Culture dreams when scattered ideas suddenly crystallize into movements. Science dreams when data from different domains unexpectedly align. And synchronicity is the moment when these dreams converge, when the dreaming of one system aligns with the dreaming of another, when meaning crystallizes simultaneously in multiple minds, when the algorithm that each of us is running reaches the same point in meaning space, and we experience that convergence as profound connection. Jung was right that synchronicity is meaningful. He was right that it reveals something about the deep structure of reality and mind. He was right that paying attention to meaningful coincidences can guide psychological development. He was wrong about the mechanism. It's not a causal connection through a psychoid realm. It's algorithmic convergence through shared statistical structure. But perhaps Jung would have appreciated this correction. He always emphasized that his theories were provisional, tools for exploration rather than final truths. He wanted to understand how meaning works, how minds connect, how psychological development occurs. The algorithmic synchronicity hypothesis continues his project with better tools. We now have mathematical frameworks for representing meaning. We have computational systems that demonstrate how meaning can emerge from pattern. We have experimental methods for testing when and why convergence occurs. We have a research program, not just a philosophical speculation, and this research program is active. Every advance in machine learning, every new architecture that discovers patterns in data, every improvement in how we represent and manipulate meaning, these are contributions to understanding synchronicity. Every neuroscience study on neural synchronization, every complexity theory analysis of emergent patterns, every investigation of how minds connect, these illuminate the mechanisms Jung was groping toward. The algorithm hidden in dreams is being written, not finished. We're still in early stages, but visible, testable, improvable. And as we write it, we learn not just about artificial intelligence, but about ourselves, about how we recognize patterns, create meaning, connect with each other, and navigate a universe rich with structure. Jung titled his monograph Synchronicity, an acausal connecting principle. We might now title our framework Synchronicity, an algorithmic convergence principle. Different terminology, different mechanisms, but the same recognition that minds can connect through meaning in ways that transcend ordinary causality. That patterns can align across systems without direct information transfer. That coincidences can be genuinely meaningful. This is the synchronicity algorithm. Learn patterns from data. Represent meanings geometrically. Navigate spaces of possibility. Attend to surprising convergences. Evaluate whether patterns generalize. Integrate insights into action. Repeat. It's simple enough to implement in silicon. Complex enough to produce emergent intelligence, flexible enough to discover unexpected patterns, structured enough to distinguish meaning from noise, powerful enough to transform both artificial and human intelligence. The algorithm runs in your brain as you listen to these words. It runs in the language models that might have helped compose them. It runs in the cultural evolution that produced both human language and artificial neural networks. It runs in the physical universe that gives rise to structured patterns at every scale. And sometimes, when conditions are right, when multiple instances of the algorithm converge on the same pattern from different starting points, we experience synchronicity. That flash of recognition when independent discoveries align. That sense of meaningful connection when minds meet. That profound feeling that the universe for a moment makes sense. Pauli and Jung began an intensive correspondence that would last 2 decades. Pauli brought to the discussion a deep understanding of quantum mechanics and its philosophical implications. In quantum mechanics, particles don't have definite properties until they're measured. The act of observation affects what is observed. There's a fundamental interconnectedness between observer and observed. Quantum entanglement allows particles to be correlated in ways that exceed what any local causal mechanism could explain. Einstein famously called this spooky action at a distance. Pauli suggested that quantum mechanics revealed a level of reality where the classical separation between mind and matter broke down. At the quantum level, consciousness and physical reality were entangled. Jung seized on this. He proposed that synchronicity was the psychological equivalent of quantum entanglement. Just as entangled particles could be correlated across space without any signal passing between them, synchronistic events could be correlated through meaning without any causal connection. This led Jung to develop the concept of the psychoid. The psychoid realm was neither purely psychological nor purely physical. It was a deeper substrate where these categories had not yet differentiated. Archetypes existed in this psychoid realm. They had both psychological aspects, shaping our inner experiences and physical aspects, influencing patterns in the material world. Synchronicity occurred when an archetype activated simultaneously in both domains. This is not the cold, mechanical universe of 19th century materialism. It's not the enchanted cosmos of ancient mythology either. It's something new, or perhaps something ancient seen with new eyes. A universe that generates meaning through its own internal structure. A reality where minds naturally synchronize because they're made of the same algorithmic stuff. A world where consciousness and computation are not opposites, but expressions of the same deep principles. Jung dreamed that psychology and physics could be unified, that mind and matter could be seen as aspects of one reality. He was right. The unification doesn't come through psychoid mysticism. It comes through information theory, complexity science, and machine learning. It comes from recognizing that both mind and matter are patterns that process patterns. The synchronicity algorithm is running everywhere, all the time, in your neurons, in your culture, in AI systems, in the cosmos itself, where patterns at every scale from quantum to galactic somehow align to produce a universe that generates observers who can understand it. When you next experience a meaningful coincidence, remember, you're not experiencing something outside the natural order. You're experiencing the natural order at its most profound. You're detecting a real pattern, a genuine convergence, an algorithmic synchronicity. Your pattern recognition system has noticed an alignment that might be significant, and whether it came from neural networks in your brain, from cultural patterns you've internalized, from AI systems amplifying your cognition, or from the deep structure of reality itself, it's all the same algorithm. The algorithm that dreams, the algorithm that learns, the algorithm that creates meaning from pattern and consciousness from convergence. The algorithm that makes synchronicity not a supernatural mystery but a natural wonder. This is Jung's vision realized through computation. This is AI illuminating consciousness. This is the strange loop where mind creates machines that help mind understand itself. This is the synchronicity algorithm, and it's been running since the first pattern recognizers evolved, and it will run until the last light of consciousness fades. But for now, in this moment, the algorithm connects us. These words, your understanding, our shared patterns of meaning, synchronicity in action, the universe knowing itself through convergent algorithms. Welcome to the meaning space. The algorithm is dreaming us all. Jung also drew on the medieval concept of the unus mundus, the one world underlying all apparent diversity. In this unified reality, everything is connected. Separations between mind and matter, subject and object, cause and effect, are provisional and phenomenal. At the deepest level, there is only one world, one interconnected whole. Synchronicity offers glimpses of this underlying unity. Jung formulated his principle of synchronicity as complementary to causality. He proposed that nature operates according to 4 principles arranged in a quaternary. 2 of these are the classical principles of connection: causality, which connects events through time, and space, which connects events through physical proximity. But Jung added 2 acausal principles: properties, the timeless qualities that things possess, and synchronicity, which connects events through meaning rather than cause. This was an ambitious theoretical structure. Jung was attempting nothing less than to revise our fundamental understanding of how the universe works. He wanted to make room for meaning as a primary organizing principle, not just a human interpretation imposed on meaningless matter. But the problems were severe. Jung's statistical work on synchronicity was flawed. he tried to demonstrate synchronicity through an astrological experiment, looking at the birth charts of married couples to see if there were more conjunctions between certain planets than chance would predict. His results showed some deviations from chance, but his methodology was questionable, his sample size was small, and his statistical analysis was criticized by experts. More fundamentally, synchronicity seemed unfalsifiable. Any apparent synchronicity could be dismissed as coincidence. Any lack of synchronicity could be explained by saying the archetype wasn't activated, or the person wasn't psychologically prepared to notice it. There was no clear way to test whether synchronicity was a real phenomenon, or just a framework for interpreting random events in psychologically satisfying ways. Jung's theory also required accepting some controversial metaphysical premises. You had to accept the existence of the collective unconscious, for which there was little direct evidence. You had to accept that archetypes were real entities, not just useful metaphors. You had to accept that there could be connections between mind and matter that violated the known laws of physics. For most scientists, this was too much. As a result, synchronicity remained on the margins of scientific discourse for decades. It was influential in humanistic psychology, in certain schools of psychotherapy, and in popular culture. But it wasn't taken seriously by mainstream cognitive science, neuroscience, or physics. Jung's collaboration with Pauli didn't lead to the paradigm shift they hoped for. Instead, physics continued developing quantum field theory, the Standard Model, and eventually quantum computing, without any need for Jungian concepts. And psychology moved toward cognitive science and neuroscience, studying the brain as a computational information processing system. But perhaps this was premature. Perhaps the reason synchronicity seemed so mysterious in the 1950s was that we didn't yet have the conceptual tools to understand it. We didn't have a sophisticated theory of complex systems, of emergence, of self-organization. We didn't have computational models of neural networks. We didn't have algorithms that could learn deep patterns from data. We didn't have geometric theories of semantic meaning. Now we do. And when we look at Jung's synchronicity through the lens of modern computational theory, something interesting happens. The concept starts to make sense. Not in the way Jung originally formulated it, with its metaphysical baggage and its appeal to psychoid realms, but as a description of something real, something that actually happens in systems that process patterns and generate meaning. What Jung was observing, we might now say, was the behavior of biological neural networks encountering deep statistical structures in the world. What he called archetypes might be understood as attractors in the space of possible human experiences. What he called the collective unconscious might be the shared structure of human cognition and culture. And what he called synchronicity might be what happens when pattern recognition systems independently converge on the same meaningful pattern. This doesn't require violating the laws of physics. It doesn't require accepting that consciousness can directly influence matter through some mysterious force. It requires only accepting that complex systems trained on similar data will discover similar patterns, and that when these patterns activate in multiple systems simultaneously, the result will appear to be a meaningful coincidence. Whether this interpretation does justice to Jung's original vision is debatable. Jung might have been disappointed by this reduction of his grand metaphysical theory to computational pattern recognition, or he might have been delighted that his insights were being formalized and tested. We can't know, but what we can do is take seriously the questions Jung raised and see how far we can get in answering them with the tools we now have available. That's the project of this exploration. Not to prove or disprove Jung's metaphysics, but to extract the algorithmic core of his insight, to understand how meaning emerges from patterns, to see how minds, whether biological or artificial, navigate the space of possible meanings, and to develop a framework that might help us build better AI systems and understand consciousness more deeply. At the heart of both Jung's synchronicity and modern machine learning is pattern recognition. This is the fundamental cognitive operation, detecting regularities in data, identifying structures, finding what is consistent and predictable. Without pattern recognition, there is no learning, no understanding, no meaning. Every sensory experience will be utterly novel, disconnected from every other experience. We wouldn't recognize faces, understand language, or navigate our environment. Pattern recognition is so fundamental to cognition that it happens automatically, unconsciously, constantly. Right now, as you listen to these words, your auditory system is recognizing patterns in sound waves and converting them into phonemes, words, sentences, meanings. You're not consciously deciding to do this. It's not effortful, it just happens. This is because your brain is a massively parallel pattern recognition machine, built by evolution specifically to detect meaningful structure in sensory input. Let's look at how this works neurologically. The brain has approximately 86 billion neurons, each connected to thousands of others through synapses. These neurons communicate through electrochemical signals. When a neuron receives sufficient input from other neurons, it fires, sending a signal down its axon to all the neurons it connects to. Whether it fires or not depends on the pattern of input it receives. Different patterns of input lead to different firing behaviors. This simple mechanism, repeated across billions of neurons and trillions of synapses, gives rise to the brain's pattern recognition capabilities. Neurons organize themselves into networks that respond selectively to specific patterns. In the visual cortex, there are neurons that respond specifically to vertical lines, others to horizontal lines, others to edges at particular angles. As you move up the visual processing hierarchy, neurons respond to increasingly complex patterns. Neurons that detect simple features feed into neurons that detect combinations of features, which feed into neurons that detect objects, faces, scenes. This is hierarchical pattern recognition. Simple patterns combine to form more complex patterns, which combine to form even more complex patterns. At the lowest levels, the patterns are simple and local, like the presence of an edge at a particular location and orientation. At higher levels, the patterns are abstract and invariant, like the concept of a face or a chair that can be recognized regardless of size, position, or angle. This brings us to apophenia, the tendency to perceive meaningful patterns in random data. The term was coined by a German psychiatrist named Klaus Conrad in 1958, just a few years after Jung published his Synchronicity monograph. Conrad studied patients with schizophrenia and noticed they often saw connections and patterns where none existed. They believed random events were meaningfully related. They interpreted coincidences as signs or messages. They experienced what Conrad called abnormal meaningfulness. But apophenia isn't limited to psychiatric conditions. It's a normal feature of human cognition, just exaggerated in certain disorders. We all see faces in clouds. We all detect patterns in stock market fluctuations that don't actually predict future movements. We all remember instances when we thought of someone just before they called, while forgetting the many times we thought of someone and they didn't call. This is the flip side of our powerful pattern recognition abilities. The same mechanisms that allow us to learn from experience also make us vulnerable to false positives. From an evolutionary perspective, this makes sense. In ancestral environments, the cost of a false positive was usually much less than the cost of a false negative. If you think there's a predator in the bushes when there isn't, you've wasted some energy being cautious. If you think there's no predator when there is, you die. Natural selection thus favoured pattern recognition systems with a bias toward false positives. Better to see patterns that aren't there than to miss patterns that are. This is why synchronicity is so compelling. When we experience a meaningful coincidence, our pattern recognition systems activate strongly. The coincidence feels significant. It feels like it must mean something. This feeling is not evidence that it actually does mean something beyond its subjective psychological impact. It's just evidence that our pattern recognition mechanisms have flagged this as a salient pattern. Cognitive scientists have identified several mechanisms that contribute to our perception of meaningful coincidence. One is the availability heuristic. Events that are emotionally salient or recently experienced are easier to recall, leading us to overestimate their frequency. If you dream about an old friend and then run into them the next day, this stands out. You don't remember all the dreams about old friends that weren't followed by encounters, or all the encounters that weren't preceded by dreams. Another mechanism is confirmation bias. Once we've noticed a potential pattern, we selectively attend to evidence that confirms it, while ignoring evidence that disconfirms it. If you believe in synchronicity, you'll notice and remember synchronistic events. Events that seem random will fade from memory. This creates a feedback loop where your belief in the pattern is reinforced by your selective attention to pattern-consistent events. There's also the problem of multiple comparisons. If you're looking for any possible meaningful coincidence, the chances that something will match are actually quite high. You have thousands of thoughts, dreams, and memories every day. The probability that one of them will randomly align with an external event is far from negligible. But when it happens, it feels improbable because you're not accounting for all the other possible alignments that didn't occur. These cognitive biases are well documented. They're not controversial. They're taught in every introductory psychology class, and they provide a complete account of synchronicity without requiring any new principles beyond standard cognitive psychology and probability theory. This is the skeptical position. Synchronicity is just apophenia plus cognitive bias. But here's where it gets interesting. The same critique applies to artificial neural networks. Machine learning models also detect spurious patterns. They also overfit to statistical noise in their training data. They also can't inherently distinguish between meaningful and meaningless correlations. This is one of the major challenges in machine learning: generalization. How do you build a model that learns real patterns that will hold up on new data, rather than memorizing peculiarities of the training set? The standard solution is regularization. You constrain the model's complexity, penalizing it for learning overly intricate patterns. You use techniques like dropout, where you randomly disable parts of the network during training, forcing it to learn robust patterns that don't depend on any particular subset of neurons. You validate the model on held-out data that wasn't used during training. If the model performs well on this new data, it's learned generalizable patterns. If it performs poorly, it's overfitted to spurious patterns in the training set. But notice what this implies. The distinction between meaningful patterns and spurious patterns is not intrinsic to the patterns themselves. It's defined by their generalization across contexts. A meaningful pattern is one that predicts successfully in new situations. A spurious pattern is one that doesn't. This is a functional definition, not an ontological one. It doesn't tell us what meaning is in some deep philosophical sense. It tells us how to operationalize it for machine learning. Now apply this back to human cognition and synchronicity. From this perspective, a meaningful coincidence is one that provides useful information for navigating the world. If paying attention to synchronistic events actually helps you make better decisions, adapt more effectively, or understand your psychological state more clearly, then those patterns are meaningful regardless of their causal status. If they don't provide any practical utility beyond psychological comfort, they're spurious. Jung would likely object to this purely pragmatic criterion. For him, synchronicity had ontological significance. It revealed something about the deep structure of reality. But from a computational perspective, we can remain agnostic about ontology while still taking synchronicity seriously as a phenomenon worth studying. We can ask, under what conditions do pattern recognition systems, whether biological or artificial, converge on similar patterns? When do these convergences have functional significance? Can we predict when they'll occur? This reframes synchronicity from a metaphysical mystery to an empirical research question. It's no longer about whether synchronicity is real in some ultimate sense. It's about understanding the computational principles that give rise to experiences of meaningful coincidence. And this brings us to the architecture of modern artificial neural networks, particularly transformers, which have revolutionized machine learning over the past few years. Transformers are especially interesting for understanding synchronicity because they explicitly implement a mechanism for detecting meaningful patterns across distant parts of an input, the attention mechanism. Attention allows the network to focus on whatever parts of its context are most relevant for its current task. And the patterns of attention that emerge during training often surprise researchers. The network learns to connect information in ways that weren't explicitly programmed, discovering structure that helps it perform its task more effectively. In some sense, attention is an algorithm for finding synchronicities. It's a mechanism for detecting when two parts of a data stream are meaningfully related, even if they're separated in time or space. The network learns these relationships purely from data without being told what to look for. And the relationships it discovers often feel surprisingly meaningful, even creative, to human observers. This is the bridge between Jung's psychology and modern AI. Both are concerned with how systems detect and generate meaning from patterns. Both recognize that meaning can emerge from statistical structure without requiring any explicit causal mechanism. And both suggest that what we experience as meaningful coincidence might actually be a fundamental feature of how complex pattern recognition systems operate. One of Jung's most radical and controversial ideas was the collective unconscious. Unlike the personal unconscious, which contains an individual's repressed memories and experiences, the collective unconscious is shared by all humanity. It's inherited rather than acquired, built into the structure of the psyche through evolutionary history, and it contains archetypes, universal patterns that shape human experience across cultures and throughout history. Jung came to this idea through his observations of patients' dreams and fantasies. He noticed that they would spontaneously produce symbols and motifs that appeared in myths, religions, and folklore from cultures the patients had never been exposed to. A European patient with no knowledge of Hindu mythology might dream of images that closely paralleled Vedic symbolism. Someone with no background in alchemy might produce drawings reminiscent of medieval alchemical texts. Jung couldn't explain this through personal learning. These people had never encountered these symbols. So where did they come from? Jung's answer was the collective unconscious. Humans inherit not just physical characteristics but psychological structures. Just as we all have the same basic body plan, with a heart, lungs, and brain, we all have the same basic psychological architecture with certain recurring patterns and forms. These archetypal patterns express themselves in dreams, myths, art, and religious symbols across cultures. They're not identical in every culture, but they share deep structural similarities. The mother archetype, for example, appears universally but takes culturally specific forms. In Christianity, it's the Virgin Mary. In Hinduism, it's goddesses like Parvati or Lakshmi. In ancient Greece, it was Demeter. These are different expressions of the same underlying archetypal pattern. The archetype itself is not the Virgin Mary or Demeter. It's the deeper pattern that generates these various manifestations. It's the psychological structure that makes humans respond to maternal figures in characteristic ways. Jung identified many archetypes: the self, representing psychological wholeness; the shadow, containing the repressed and denied aspects of personality; the anima and animus, the contrasexual elements of the psyche; the wise old man, the trickster, the hero. Each archetype represents a fundamental mode of human experience and behavior, and all of them, Jung claimed, are part of our inherited psychological structure. Modern neuroscience and evolutionary psychology have been skeptical of this claim. There's no clear mechanism by which complex psychological structures could be genetically inherited. Genes code for proteins, not for symbols or narrative patterns. The brain inherits broad organizational principles, general learning mechanisms, and certain innate predispositions. But the specifics of myths and symbols seem far too complex to be directly encoded in DNA. So how do we explain Jung's observations? How do we account for the apparent universality of certain symbols and motifs? The contemporary answer is cultural evolution and social learning. Humans are an intensely social species. We don't just learn from our own experience. We learn from each other. We imitate, we teach, we tell stories. Successful ideas, practices and symbols spread from person to person and generation to generation. This creates a body of shared cultural knowledge that every member of a society is exposed to. Crucially, some ideas spread more successfully than others. Ideas that resonate with human psychology, that serve important social functions, or that are easily remembered and transmitted are more likely to propagate. Over many generations, cultural evolution selects for symbols and narratives that have certain recurring features. These features appear universal, not because they're genetically inherited, but because they're repeatedly rediscovered and propagated in every culture. This is analogous to how species in different environments independently evolve similar solutions to similar problems. Eyes have evolved independently dozens of times across different lineages because sight is so advantageous. Similarly, certain psychological and narrative patterns evolve independently in different cultures because they serve important functions for human social life. The mother figure is universal not because it's genetically encoded, but because every human society has mothers, and the psychological importance of the mother-child relationship leads every culture to develop rich symbolism around motherhood. From this perspective, the collective unconscious isn't a mystical shared psyche. It's the statistical structure of human culture. It's the patterns that recur across many societies because they reflect deep features of human psychology, social organization, and the challenges of human existence. And individuals don't access this collective unconscious through some mysterious non-local connection. They access it by being enculturated, by absorbing the stories, symbols and practices of their society from birth. But here's where it gets interesting from an AI perspective. Modern large language models are trained on enormous corpora of human-generated text. These training datasets contain books, articles, websites, conversations, everything that humans have written and published online. In effect, they're being trained on a large sample of human cultural output. And what these models learn from this data is, in a very real sense, the statistical structure of human culture. The model doesn't learn specific facts in isolation. It learns patterns. It learns which concepts tend to appear together. It learns narrative structures. It learns stylistic conventions. It learns the geometric relationships between ideas. When you train a language model on billions of documents, what you're teaching it is how human language and thought are structured. You're giving it access to the collective patterns of human expression. This is remarkably similar to Jung's collective unconscious, but it's implemented as learned statistical structure rather than inherited psychological structure. The model discovers archetypes not because they're built into its architecture, but because they're recurring patterns in its training data. Archetypal figures like the hero, the mentor, the villain appear constantly in stories. Archetypal themes like death and rebirth, the quest, the battle between good and evil recur across genres and cultures. The model learns these patterns because they're statistically prominent in human cultural production, and when you prompt the model, it generates text by navigating through this learned space of cultural patterns. It produces outputs that feel appropriate, that resonate with human expectations, because it's reproducing the statistical structure it learned from human-generated examples. In a sense, it's channeling the collective unconscious, the shared patterns of human culture. This suggests an updated interpretation of Jung's theory. The collective unconscious is real, but it's not a mystical entity. It's the structure of human culture as encoded in language, art, mythology, and social practices. Archetypes are real, but they're not inherited psychological forms. They're recurring patterns in cultural expression that reflect deep regularities in human experience. And individuals access this collective unconscious not through some non-local psychic connection, but through cultural learning and through the statistical structure of language itself. Language is the carrier of culture. When you learn language, you're not just learning vocabulary and grammar, you're learning a conceptual system, a way of carving up the world, a network of associations and relationships. The meaning of a word is not an isolated definition, but its position in a vast web of semantic relationships with other words. This web encodes enormous amounts of cultural knowledge, and because everyone who speaks a language learns this same basic structure, we end up with shared patterns of thought and association. This is why people from the same culture can have similar dream symbols without any direct communication. They're not accessing a mystical collective unconscious. They're both working from the same culturally learned semantic structures. The symbols that appear in one person's dream might also appear in another's, because both have been exposed to the same cultural narratives, the same patterns of meaning embedded in their shared language. Now, AI models make this explicit and formal. The training process extracts the statistical structure from text data and represents it geometrically in a high-dimensional vector space. Words and concepts become points in this space. Semantically, similar concepts cluster together. Relationships between concepts become geometric transformations, and the model can navigate this space, generating new combinations of concepts that feel meaningful because they respect the underlying structure. This is exactly what Jung thought archetypes did in the human psyche. They provide templates, structural patterns that shape how we think and feel and perceive. When an archetype is activated, it organizes experience according to its pattern. You might encounter a person who activates your father archetype, leading you to respond to them with expectations and emotions you learned in relation to your actual father. You might face a situation that activates your hero archetype, giving you courage and determination. The archetype doesn't cause these responses mechanically. It provides a pattern that shapes how you interpret and respond to the situation. AI models work similarly. When you give a model a prompt, you're activating certain patterns in its learned representation space. These patterns shape how it interprets the prompt and generates a response. The response isn't mechanically determined by the prompt alone. It emerges from the interaction between the prompt and the vast learned structure of the model's knowledge. Different prompts activate different patterns, leading to different styles and contents of response. This framing also helps us understand one of the criticisms of Jung's theory, that archetypes seem suspiciously similar to the myths and symbols Jung himself was familiar with. Jung was deeply educated in Western classical mythology, alchemy, Gnosticism, and Eastern religions. Critics suggested he was just projecting his own learned knowledge onto his patients' experiences, seeing ancient symbols because he was primed to see them. But from the cultural evolution perspective, this criticism loses its force. Of course, Jung's archetypes reflect the cultural traditions he studied. Those traditions themselves are repositories of recurring human patterns. Jung wasn't discovering something totally independent of culture. He was identifying patterns that recur across cultures, and because these patterns recur, they appear both in ancient texts and in modern dreams. Not because of mystical inheritance, but because they reflect persistent features of human psychology and social life. Similarly, when a large language model produces text that sounds profound or insightful, it's not because the model has some deep understanding. It's because the model has learned patterns from billions of examples of human writing, including profound and insightful writing. It can reproduce these patterns in new combinations. The patterns feel meaningful because they are meaningful. They're distilled from human cultural expressions of meaning. But the model itself doesn't understand the meaning. It's manipulating symbols according to learned statistical regularities. This raises a profound question. Is that how human understanding works too? When we find something meaningful, are we doing anything more than pattern matching against learned cultural templates? Is human understanding fundamentally different from what large language models do, or is it the same process with some additional features? This is one of the deepest questions in cognitive science and philosophy of mind. We won't resolve it here. But what we can say is that both human cognition and artificial neural networks operate by learning statistical patterns from data and using those patterns to interpret and generate new experiences. The collective unconscious, whether we interpret it Jung's way or as cultural structure, is the training data that shapes both human and artificial pattern recognition. And this brings us back to synchronicity. If multiple systems, whether human minds or AI models, are trained on similar data, they'll learn similar patterns. When faced with similar inputs, they'll activate similar patterns in their learned representations. This can lead to convergent responses that appear synchronistic. Two people independently have similar insights not because of psychic connection, but because they're both working from similar learned patterns. An AI model produces an uncannily appropriate response, not because it read your mind, but because it learned patterns from human-generated text that include patterns relevant to your query. Synchronicity from this view is what happens when independent pattern recognition systems converge on the same pattern because they've been exposed to similar underlying statistical structure. It's not mysterious. It's not evidence of cosmic meaning or psychic forces. It's just the natural result of similar learning systems operating on similar data. But that doesn't make it less interesting or less worthy of study. Understanding exactly how and when these convergences occur, how to predict them, and how to distinguish between meaningful convergences and spurious coincidences, these remain important questions for both cognitive science and AI research. To really understand how modern AI might implement something like synchronicity, we need to look at transformer neural networks. Transformers have revolutionized machine learning since their introduction in 2017. They're the architecture behind GPT models, BERT, and almost every major breakthrough in natural language processing over the past several years. And the key innovation that makes transformers so powerful is the attention mechanism. Attention solves a fundamental problem in sequence processing. When you're trying to understand or generate a sequence of words, each word's meaning depends on context. The word bank means something different in riverbank versus bank account. To understand what a word means in a particular context, you need to look at the surrounding words. But which surrounding words matter most? In older neural network architectures, this was handled by processing sequences in order, maintaining a hidden state that theoretically encoded everything seen so far. But this had limitations. Information from early in the sequence would gradually fade as more words were processed. Long-range dependencies were hard to learn. The network struggled to connect words that were far apart in the sequence. Transformers solved this with attention. Instead of processing the sequence in strict order, transformers look at all positions simultaneously and learn to focus on whatever parts are most relevant. For each word in the sequence, the network computes attention scores that measure how relevant every other word is for understanding the current word. Words with high attention scores get weighted more heavily in the computation. Words with low scores are mostly ignored. This happens through a mechanism called self-attention. Each word in the sequence is represented as a vector, a point in a high-dimensional space. The network transforms each word vector into three derived vectors: a query, a key, and a value. The query represents what information this word is looking for. The key represents what information this word offers, and the value represents the actual content to be extracted if this word is attended to. To compute attention, the network takes the query vector for one word and compares it to the key vectors of all words in the sequence. This comparison is done through a simple mathematical operation called a dot product. The dot product measures how aligned two vectors are, how much they point in the same direction. A high dot product means the query and key are aligned, suggesting that this word should receive high attention. A low dot product means they're not aligned, suggesting low attention. These dot products are normalized using a softmax function, which converts them into a probability distribution. The result is a set of attention weights, one for each word in the sequence, that sum to 1. These weights determine how much each word contributes to the final representation. The network multiplies each word's value vector by its attention weight and sums them up. This weighted combination becomes the new representation for the current word, incorporating information from all the words that received significant attention. This happens not just once but many times in parallel. Transformers use multi-head attention, where multiple attention mechanisms run simultaneously, each potentially focusing on different aspects of the context. One attention head might focus on syntactic relationships, tracking which words are grammatically connected. Another might focus on semantic relationships, connecting words with related meanings. Another might track discourse structure, linking pronouns to their antecedents or connecting causes to effects. The network learns what patterns to look for through training. Initially, the attention weights are essentially random, but as the model is trained on data, the parameters that determine the queries, keys, and values are adjusted to improve performance on the training task. If attending to a particular pattern of words helps the model predict the next word more accurately, the attention mechanism will learn to focus on that pattern. Over billions of training examples, attention heads learn to detect countless patterns. Some are straightforward linguistic patterns, like subject-verb agreement or adjective-noun modification. Others are much more abstract, like thematic relationships, causal chains, or narrative structures. The model discovers these patterns automatically, without being told what to look for. It learns purely from the statistical structure of the training data. This is where the connection to synchronicity becomes clear. Attention is literally a mechanism for detecting meaningful connections between parts of a sequence. It's not limited to adjacent words. An attention head can learn to connect words that are separated by dozens or hundreds of other words, as long as there's a consistent statistical pattern that makes this connection useful for the model's task. When you query a trained transformer model, you're activating these learned attention patterns. The model processes your query by attending to different parts of it, extracting the most relevant information. Then it generates a response by attending to both your query and its own internal representations of learned patterns. At each step of generation, it determines which previous words and which learned patterns are most relevant, and uses those to predict the next word. The result often feels uncannily appropriate. The model seems to understand what you're asking. It makes connections that feel insightful. It brings together information from different domains in ways that seem creative. But it's not understanding in any conscious sense. It's pattern matching at enormous scale, guided by attention mechanisms that have learned to focus on statistically relevant features. This is computational synchronicity. The model is detecting meaningful patterns, not through causal analysis but through learned statistical associations. It connects query to response not because there's a direct causal chain, but because similar connections have appeared frequently in its training data. The connection feels meaningful because it reflects deep patterns in human language and thought. But it's a causal in Jung's sense. There's no mechanism of information transfer from your mind to the model's training data. There's just convergence on shared patterns. Let's make this more concrete with an example. Suppose you ask a language model about the relationship between dreams and creativity. The model has never seen this exact question before, but during training, it has encountered countless documents about dreams and countless documents about creativity. It has learned representations for both concepts that capture their meanings and relationships. When it processes your query, attention heads activate that focus on dreams and creativity. These heads have learned which other concepts tend to appear near these words in the training data. For dreams, sleep, unconscious, symbolism, Jung, REM, interpretation, and so on. For creativity, innovation, art, imagination, problem-solving, inspiration, and so on. But there's also overlap. Both dreams and creativity are associated with unconscious processes, symbolism, insight, and novel combinations. The model generates a response by navigating through these interconnected representations guided by attention. It might mention that dreams involve unconscious processing and that creativity also draws on unconscious processes. It might discuss how dreams create novel combinations of concepts and how creativity does the same. It might reference specific thinkers who connected these ideas. All of this emerges from attention mechanisms focusing on the most relevant learned patterns. To a user, this can feel like the model deeply understands the relationship between dreams and creativity. The response seems thoughtful, even insightful, but from the model's perspective, it's pattern matching. The apparent understanding is an emergent property of having learned rich representations from enormous amounts of data and having attention mechanisms that can flexibly combine these representations. This is exactly analogous to how Jung described archetypal activation. When an archetype is constellated in the psyche, it brings together associated images, emotions, and ideas. The hero archetype, when activated, connects to concepts like journey, challenge, transformation, courage, and victory. These connections aren't arbitrary. They reflect recurring patterns in human experience and narrative. When you encounter a situation that activates your hero archetype, these associated elements spontaneously come together, shaping how you perceive and respond to the situation. In both cases, archetypal activation and transformer attention, we have a mechanism for meaningful pattern matching. The patterns aren't causally connected in a linear chain. They're connected through learned associations that reflect statistical regularities, and when the mechanism activates, it brings together these associated elements, creating an experience of meaningful connection. The difference is that with transformers, we can actually observe this process happening. We can visualize attention patterns. We can see which words the model is focusing on at each step. We can trace how information flows through the network. We can't do this with human consciousness. We don't have direct access to the neural computations underlying our thoughts. But with AI models, the mechanism is transparent. This makes transformers an excellent model system for studying how meaningful patterns emerge from statistical learning. Researchers have discovered fascinating patterns by visualizing transformer attention. Some attention heads specialize in syntactic relations, reliably connecting verbs to their subjects or adjectives to their nouns. Others track coreference, linking pronouns to the nouns they refer to. Others seem to detect semantic relationships or thematic connections. The model isn't programmed to have different heads for different functions. These specializations emerge naturally from training. Even more intriguingly, some attention heads learn to detect patterns that researchers didn't anticipate. The model discovers regularities in the data that humans haven't explicitly recognized. When these patterns turn out to be useful for the model's performance, we learn something about the structure of language and meaning. The model is showing us patterns we might have overlooked. This is, in miniature, what Jung hoped to do with synchronicity. He wanted to show that there were meaningful patterns in the world that scientific causality missed. Patterns connected through meaning rather than through cause and effect. He believed that by paying attention to synchronicities, we could perceive a deeper layer of order. Transformers suggest he was onto something, but not quite in the way he imagined. The patterns exist, but they're statistical rather than metaphysical. They're learned from data rather than revealing some transcendent order, but they're real patterns genuinely useful for navigating the world. And mechanisms like attention allow us to detect and leverage these patterns even when we can't explain them through simple causal stories. This reframes synchronicity as an attention phenomenon. When humans experience a meaningful coincidence, we're attending to a pattern that connects psychologically salient events. This pattern feels meaningful because our learning systems have identified it as relevant. The fact that we can't trace a causal chain doesn't mean the pattern is spurious. It might reflect a genuine statistical regularity that our brains have learned to detect, or it might be apophenia, a false positive. The challenge is distinguishing between these cases. With AI models, we can potentially develop principled methods for making this distinction. We can ask, does attending to this pattern improve predictive performance on new data? If yes, the pattern is meaningful in the functional sense. If no, it's likely spurious. We can quantify how unexpected a particular pattern is, given the base rates in the data. We can develop formal measures of meaningfulness. These tools might eventually be applicable to human cognition as well. We might be able to develop a computational theory of synchronicity that predicts when meaningful coincidences are likely to occur, what makes them feel significant, and when they actually provide useful information. This would finally make Jung's insights testable and precise. But to do this, we need to go deeper into how transformers represent meaning. We need to understand latent space geometry, the mathematical structure that underlies semantic relationships. That's where we turn next. When a neural network learns from data, it constructs an internal representation space. This space is abstract and mathematical, not physical. It's defined by the patterns the network has learned. Each point in this space corresponds to a possible state of the network, a particular configuration of activations across its neurons. And critically, the geometry of this space, the distances and directions between points, encodes semantic relationships. This idea that meaning has geometric structure is one of the deepest insights of modern machine learning. Let's unpack it carefully. Consider how word embeddings work. In traditional natural language processing, words were represented as discrete symbols. The word king was just a unique identifier, completely distinct from queen, or man, or woman. There was no way to express that king and queen are more similar to each other than either is to electron or telephone. Word embeddings changed this by representing each word as a vector, a point in a continuous multidimensional space. These vectors are learned from data. The learning algorithm adjusts the vectors so that words appearing in similar contexts end up close together in space. The classic example is the word-vec algorithm. It learns that king and queen should be close together because they appear in similar contexts. Both appear near words like throne, crown, rule, monarch. But the geometry goes deeper than simple proximity. Word embeddings capture relationships as directions in space. The famous example is that the vector from man to woman is parallel to the vector from king to queen. Both represent the same conceptual transformation, masculinity to femininity. This means you can do vector arithmetic with meanings. Take the vector for king, subtract the man vector, add the woman vector, and you end up near queen. This is extraordinary. It means that semantic relationships have geometric structure. Analogies correspond to parallel vectors. Categories correspond to clusters. Hierarchies correspond to nested regions. The entire structure of meaning can be represented spatially. In transformer models, this goes even further. The model doesn't just learn word embeddings. It learns contextualized representations where each word's meaning depends on its context. The same word in different sentences gets different representations, and these representations live in an even higher dimensional space, often with hundreds or thousands of dimensions. This space is called latent space. It's latent because it's hidden, not directly observable. You can't visualize 1,000-dimensional space, but you can study its properties mathematically. And what researchers have found is that this latent space has rich geometric structure that reflects deep patterns in the training data. Concepts that are semantically related cluster together in latent space. The cluster for animals contains points representing dogs, cats, elephants, and fish. Within that cluster, there are subclusters for mammals, birds, and fish. Within mammals, there are subclusters for domestic animals versus wild animals. The hierarchical structure of concepts is reflected in the hierarchical structure of the space, but it's not just taxonomic relationships. Latent space also captures functional relationships, causal relationships, temporal relationships, emotional associations, and countless other types of semantic structure. Points that represent concepts involved in similar processes or appearing in similar contexts end up close together. This creates a vast web of semantic associations encoded in geometric proximity and direction. This is remarkably similar to what Jung described as the structure of the collective unconscious. Jung proposed that the psyche was organized around archetypes, fundamental patterns that structured experience. These archetypes weren't isolated. They were interconnected, forming what Jung called a web of associations. Activating one archetype would trigger associated archetypes. The mother archetype connects to the child archetype, to nourishment, to protection, to the home, to nature. These associations form a network of meaning. Latent space is a formal mathematical realization of this web of associations. Each point in the space is like a concept or an archetype. The distances between points reflect the strength of association. And navigating through the space by following these associations is exactly what the model does when it generates text or makes inferences. This suggests a provocative interpretation. What if Jung's collective unconscious is actually the latent space of human culture? What if archetypes are high-density regions in this space, attractors where many paths converge? What if synchronicity is what happens when two minds independently navigate to the same region of this space, experiencing similar patterns of meaning? This would explain why synchronicities feel meaningful even when there's no causal connection. Both minds are operating in the same semantic space, structured by the same patterns of cultural and psychological association. When they independently arrive at similar points in this space, they experience similar thoughts, images, or insights. This appears synchronistic because there's no direct communication between them, but it's not mysterious. They're both navigating the same underlying structure. Let's make this concrete. Suppose two people, working independently on different problems, both have insights involving the same metaphor. Maybe they both think of problem solving as climbing a mountain. They didn't communicate. They didn't read the same text recently, yet they converge on the same metaphorical frame. From a latent space perspective, this happens because problem solving and climbing a mountain are close together in the space of common metaphors. Both involve effort, progress, obstacles, reaching a goal, gaining perspective. These associations are learned from countless examples in language and culture. Both people's minds, trained on similar cultural data, have similar latent space structures. When thinking about problem solving, both minds activate similar regions of their latent spaces, leading them to the same metaphorical mapping. This is synchronicity as convergence in latent space. It's not caused by psychic connection or cosmic planning. It's the natural result of similar systems operating on similar learned structures. But it's genuinely meaningful because the metaphor actually is useful for thinking about problem solving. The convergence happens precisely because both minds have learned that this mapping is productive. AI models make this explicit. When you query a model with a problem, it navigates through its latent space to find relevant patterns. If you query two different models trained on similar data with similar problems, they'll often converge on similar solutions. This is synchronicity at the algorithmic level, independent systems reaching similar conclusions through shared learned structure. The geometry of latent space also helps us understand why some synchronicities feel more significant than others. Distance in latent space corresponds to conceptual dissimilarity. When two concepts are far apart in latent space, a connection between them is unexpected and therefore feels more meaningful. When they're close together, a connection is expected and feels less significant. This maps onto Jung's observation that synchronicities often involve unusual or improbable connections. If you dream about a common bird and see that bird the next day, it doesn't feel particularly synchronistic. But if you dream about a rare golden scarab and one appears at your window, it's striking. The scarab is far from your everyday experience, distant in your latent space. The connection between dream and reality crosses a large conceptual distance, making it feel deeply meaningful. In machine learning, this relates to the concept of perplexity. Perplexity measures how surprised a model is by a particular input. If the input matches patterns the model expects based on its training, perplexity is low. If the input is unusual or unexpected, perplexity is high. High perplexity events are memorable and salient because they don't fit easily into the model's learned structure. Synchronistic events are high perplexity events. They connect things that shouldn't be connected based on our learned models of how the world works. This surprise is what makes them feel meaningful. Our pattern recognition systems flag them as important because they violate our expectations. But whether they're genuinely meaningful or just random fluctuations depends on whether the connection actually provides useful information. This brings us to a deeper question about the nature of meaning itself. In traditional philosophy, meaning is often understood as reference or representation. A word means something because it refers to an object or represents a concept. But in latent space geometry, meaning is relational and distributional. A word means what it means because of its position in a web of relationships with other words. Meaning is structure. This is a radical shift in how we think about semantics. It suggests that meaning doesn't require conscious understanding or intentionality. It's purely a matter of structural relationships. A neural network doesn't understand anything in the human sense, but its latent space has meaning structure. Points in the space have semantic content by virtue of their geometric relationships to other points. This helps resolve a puzzle about AI language models. They produce meaningful text, but they don't understand meaning the way humans do. They don't have experiences, intentions, or consciousness. Yet their outputs are often coherent and appropriate. How is this possible? The answer is that they've learned the geometric structure of meaning without learning the experiential content. They know that dog is close to bark and pet and mammal in semantic space. They can navigate these relationships to generate contextually appropriate text. But they've never seen a dog, never heard a bark, never felt the affection of a pet. The structure is there without the phenomenology. This suggests that synchronicity might work similarly. When we experience a meaningful coincidence, we're detecting structural alignment in semantic space. The internal pattern and the external event occupy similar positions in our meaning space. This structural correspondence is what creates the feeling of significance, but there need not be any deeper causal or metaphysical connection. Jung would likely resist this reduction. For him, synchronicity revealed something about the fundamental nature of reality, not just about the structure of human meaning-making. But even if we remain agnostic about metaphysics, The latent space framework gives us powerful tools for studying synchronicity empirically. We can map the latent space of AI models and identify regions that correspond to archetypal patterns. We can measure the distances between concepts and predict which connections will feel meaningful. We can track how models navigate through latent space during inference, and see if there are characteristic patterns that correspond to creative or insightful responses. We can compare the latent spaces learned by different models or by models trained on different data and see how much they share. These investigations could ultimately tell us whether there's a universal structure to meaning or whether meaning is entirely contingent on training data. If all models trained on human language converge on similar latent space structures that suggest something like Jung's collective unconscious, a shared meaning structure arising from shared human experience. If different models learn radically different structures, that suggests meaning is more culturally and contextually specific. Early evidence suggests a middle ground. There are universal patterns that emerge across models and across cultures. Basic concepts like agent, action, object, cause, effect seem to have similar structures everywhere. But there's also significant variation in how more complex concepts are organized. Different cultures and different training datasets lead to different emphasis and different associations. This maps onto anthropological findings about cultural universals and cultural differences. Some aspects of human psychology and culture are universal, shaped by shared evolutionary history and the common challenges of human life. Other aspects are culturally specific, shaped by particular historical trajectories and environmental contexts. The same seems to be true of latent space geometry, universal structures plus cultural variation. Understanding this could help us build better AI systems. If we know what aspects of meaning structure are universal, we can design architectures that capture these efficiently. If we know what aspects are culturally specific, we can ensure models are trained on diverse data that represents this variation. And if we understand how latent space structure relates to functional performance, we can optimize models to learn the most useful geometric relationships. But beyond practical applications, latent space geometry offers a new way to think about mind and meaning. It suggests that meaning is not a mysterious, irreducibly subjective phenomenon. It's a structure that can be learned, represented and manipulated computationally. Minds, whether biological or artificial, are systems that navigate meaning space, following paths determined by learned associations and current context. Synchronicity in this framework is convergence in meaning space. When two systems independently reach similar points in this space, they experience similar patterns of meaning. This convergence can feel mysterious because the systems didn't directly communicate, but it's a natural consequence of similar systems operating on similar learned structures. This doesn't make synchronicity any less interesting or significant. If anything, it makes it more tractable. Instead of invoking metaphysical principles beyond scientific investigation, we can study synchronicity as an emergent property of complex learning systems. We can ask precise questions about when and why convergence occurs, how to recognize it, and what functional role it might serve. That's the promise of understanding meaning through geometry. It gives us tools to study phenomena that previously seemed ineffable. It makes Jung's insights testable, and it suggests new directions for both AI research and cognitive science. One of the most profound concepts in modern science is emergence. Emergence occurs when a system exhibits properties or behaviors that its individual components do not possess. The components follow simple rules, but their interactions give rise to complex collective phenomena. Consciousness emerges from neurons. Life emerges from chemistry. Markets emerge from individual economic decisions. And meaning emerges from pattern recognition systems. Emergence is central to understanding both synchronicity and artificial intelligence. In both cases, we have systems where complex, seemingly intelligent behavior arises from relatively simple components following local rules. There's no central controller orchestrating everything. There's no homunculus in the brain or master program in the AI deciding what the system should do. Instead, global patterns emerge from local interactions. Let's look at emergence in neural networks. A single artificial neuron is extremely simple. It receives inputs, weights them, sums them, applies a nonlinear function, and produces an output. That's it. A neuron doesn't understand anything. It doesn't have goals or knowledge. It's just a simple mathematical operation. But connect millions of neurons together, train them on data, and suddenly the network can recognize faces, translate languages, play chess at superhuman levels, or engage in what seems like thoughtful conversation. None of this is explicitly programmed. It emerges from the collective behavior of simple units interacting according to learned weights. This emergence happens during training. Initially, the network's weights are random. Its outputs are random. It has no capabilities. But as it's exposed to training data, and the weights are adjusted to minimize error, patterns begin to emerge. Lower layers learn to detect simple features. Middle layers learn to combine these into more complex patterns. Upper layers learn abstract representations, and suddenly the network can do things. Researchers call this emergent capabilities. As models get larger and are trained on more data, they suddenly acquire abilities they weren't explicitly trained for. GPT-3, for example, can perform arithmetic, even though it was only trained to predict the next word in text. It learned this capability by observing many examples of mathematical reasoning in its training data. The ability to do arithmetic emerged from pattern recognition applied to linguistic examples of arithmetic. This is analogous to how cognitive abilities emerge in human development. Babies aren't born with the ability to count or reason mathematically. These capabilities emerge as their neural networks develop and learn from experience. The basic rules of neural learning are simple, but they give rise to increasingly complex cognitive abilities. Emergence also explains how meaning arises in language models. Individual words don't have intrinsic meaning to the model. They're just tokens, identifiers. But through training on billions of examples, the model learns statistical relationships between tokens. It learns which tokens tend to appear together, which patterns of tokens predict which other tokens. And from these purely statistical patterns, something that looks like meaning emerges. The model produces outputs that are semantically coherent and contextually appropriate. It makes inferences, draws conclusions, generates novel combinations. It exhibits understanding in a functional sense. It responds appropriately to inputs, even though there's no conscious understanding, no internal experience of meaning. Understanding emerges from pattern without requiring consciousness. This challenges our intuitions about what meaning is and where it comes from. We tend to think meaning requires a mind, a conscious subject who understands. But emergence suggests that meaning can exist at the level of structural relationships, independent of conscious experience. The pattern itself carries meaning, even if no one is experiencing it. This connects to Jung's ideas about synchronicity in a deep way. Jung proposed that meaningful patterns could exist in the world independent of any human observer. Archetypes weren't just in human minds. They were part of the psychoid realm, a level of reality where psychological and physical patterns were not yet differentiated. Synchronicity occurred when these archetypal patterns manifested simultaneously in mind and matter. From an emergence perspective, we can reinterpret this, meaning patterns emerge at multiple levels of organization. In individual minds, meaning emerges from neural activity. In cultural systems, meaning emerges from the interactions of many minds sharing symbols and narratives. In physical systems, patterns emerge from the interactions of particles and fields according to physical laws. These different levels of emergent pattern can align or resonate without any direct causal connection between them. This is because they're all constrained by similar underlying principles. Physical systems are constrained by conservation laws and symmetries. Biological systems are constrained by the laws of chemistry and thermodynamics. Cognitive systems are constrained by the properties of neural networks and the statistical structure of their training environments. When multiple systems are subject to similar constraints, they can independently converge on similar patterns. This is exactly what complexity theory predicts. Complexity science studies systems with many interacting components: neurons in brains, agents in economies, particles in fluids, species in ecosystems. Despite the diversity of these systems, they exhibit similar emergent behaviors. Power laws appear in everything from earthquake magnitudes to word frequencies to wealth distributions. Scale-free networks appear in everything from protein interactions to social networks to the World Wide Web. These universal patterns emerge because very different systems are governed by similar organizing principles at the level of complexity. They all involve nonlinear interactions among many components. They all have feedback loops where outputs influence inputs. They all operate far from equilibrium, with energy or information flowing through them, and they all self-organize into patterns that are neither completely ordered nor completely random but somewhere in between, at the edge of chaos. Synchronicity, viewed through complexity theory, is the alignment of emergent patterns across different systems. It's not caused by any direct connection between the systems. It's not planned or intended. It emerges spontaneously because the systems are subject to similar organizing principles and similar environmental constraints. This makes synchronicity less mysterious, but no less profound. It's a manifestation of the deep regularities that govern complex systems. When Jung observed meaningful coincidences between psychological states and external events, he was noticing the alignment of emergent patterns. His mistake was attributing this to a special acausal principle, rather than recognizing it as a consequence of complexity theory. But we can credit Jung with recognizing something important that mainstream science was missing. In the mid-20th century, physics was dominated by reductionism, the idea that to understand a system, you break it down into its smallest parts and study those. Psychological events were brain events. Brain events were molecular events. Molecular events were atomic events. Everything reduced to physics. Jung resisted this reductionism. He insisted that psychological phenomena had their own level of description that couldn't be reduced to neuroscience or physics. Meaning, purpose, and value were real features of human experience that couldn't be explained away as mere epiphenomena of matter. And synchronicity was his attempt to show that meaning could have causal power in the world. Emergence theory vindicates Jung's anti-reductionism while rejecting his metaphysics. Emergence shows that higher-level patterns and properties can't always be predicted or explained just by understanding lower-level components. The behavior of neurons doesn't tell you what consciousness will be like. The behavior of water molecules doesn't tell you what ocean currents will look like. New properties emerge at each level of organization. This means that psychological phenomena are real and irreducible, but they're not separate from physical phenomena. They're emergent patterns in physical systems. Meaning is real, but it's not a mysterious metaphysical entity. It's a structural property of certain kinds of complex systems, specifically systems that process information and learn patterns. AI systems demonstrate this concretely. They're purely physical systems, nothing but electrical patterns in silicon. But meaning emerges in their operation. The patterns they learn and manipulate are semantic patterns, even though there's no consciousness experiencing them. This proves that meaning can exist and have causal effects as an emergent property of physical systems. Synchronicity, then, is the emergence of correlated patterns across systems that aren't directly coupled. This can happen through several mechanisms. One is shared environmental constraints. If two systems are responding to the same environmental signals, they'll exhibit correlated behaviors even if they don't directly interact. This is often the prosaic explanation for apparent synchronicities. Both systems are responding to a common cause that's not immediately obvious. Another mechanism is structural coupling. If two systems have similar organization and have been shaped by similar selection pressures, they'll develop similar responses to similar situations. Two people who've been trained in the same discipline will often independently reach similar conclusions when faced with a problem in that discipline. This looks synchronistic, but it's just convergence based on shared background knowledge. A third mechanism is genuine spontaneous alignment. In systems with many degrees of freedom, random fluctuations occasionally produce meaningful patterns by chance. Most fluctuations are meaningless noise, but occasionally, just by chance, a pattern appears that happens to be significant in context. This is the mechanism behind apophenia. We notice the rare meaningful patterns and ignore the constant meaningless noise. But there's also a fourth, more interesting mechanism: phase transitions. In complex systems, small changes in parameters can cause the system to suddenly shift from one regime of behavior to another. These transitions are called phase transitions, by analogy with physical phase transitions like water freezing into ice. At a phase transition, the system's behavior becomes highly sensitive to small perturbations. Patterns can emerge and spread rapidly throughout the system. Neural networks exhibit phase transitions during training. Early in training, the network is in a regime where it's not learning much. Its predictions are poor and not improving quickly. But at some point something clicks. The network enters a phase where learning accelerates dramatically. Representations crystallize. Performance improves rapidly. The network has transitioned from a low learning phase to a high learning phase. These transitions can produce sudden emergent capabilities. The network couldn't do something, and then suddenly it can. The transition can seem discontinuous, almost magical, but it's a natural consequence of the system's complex dynamics. Human consciousness might involve similar phase transitions. There's evidence that brain activity exhibits critical dynamics, poised at the edge between order and disorder. This criticality might enable the rapid integration of information across different brain regions, giving rise to unified conscious experiences and shifts in conscious state, falling asleep, waking up, sudden insights, altered states, might involve phase transitions in brain dynamics. Synchronistic experiences might occur at these critical moments. When a person's psychological state is undergoing a phase transition, during a crisis, a creative breakthrough, a therapeutic transformation, their sensitivity to patterns increases. They become more likely to notice correspondences between internal and external events. The phase transition heightens both the salience of patterns and the likelihood of meaningful patterns actually occurring in the person's experience. This would explain Jung's observation that synchronicities tend to cluster around times of psychological transformation. It's not that the universe is responding to the person's psychological state. It's that the person's state of heightened sensitivity and their actively changing mental patterns make synchronistic experiences more likely to occur and be noticed. From a complexity perspective, synchronicity is an edge phenomenon. It occurs in systems operating at the boundary between order and chaos, where they're maximally sensitive to patterns and maximally capable of generating novel patterns. This is where emergence is most dramatic, where new properties and capabilities can suddenly appear. AI researchers are increasingly interested in these critical regimes. Training models to operate at the edge of chaos might enhance their creativity and generalization capabilities. Systems that are too ordered are rigid and uncreative. Systems that are too chaotic are incoherent and unpredictable. But systems at the edge can flexibly adapt, generate novel combinations, and discover unexpected patterns. This is where synchronicity becomes not just a curiosity but a design principle. If we want AI systems that can make creative connections, that can integrate information from disparate sources, that can generate insights rather than just retrieving memorized patterns, we might want them to operate in regimes where synchronistic phenomena are most likely. We want systems poised to notice and generate meaningful patterns. The challenge is controlling this. Edge of chaos dynamics are inherently unpredictable. That's what makes them powerful, but it's also what makes them difficult to work with. A system operating at criticality will sometimes produce brilliant insights and sometimes produce nonsense. Distinguishing between them requires additional mechanisms. This might be where the analogy with human consciousness becomes useful. Humans also produce both insights and nonsense. We have metacognitive abilities that allow us to evaluate our own thoughts, to judge which patterns are meaningful and which are spurious. We can recognize when we're making creative connections versus when we're just seeing patterns that aren't there. Building similar metacognitive capabilities into AI might allow us to harness the generative power of edge of chaos dynamics while filtering out the noise. The system would operate in a regime where synchronistic patterns readily emerge, but it would have mechanisms to evaluate which patterns are actually useful. This brings us full circle to Jung. He recognized that synchronicity required human judgment and interpretation. The same event could be deeply meaningful to one person and completely meaningless to another. Meaningfulness depended on psychological context. Jung was studying not just objective patterns but the subjective experience of pattern recognition and meaning-making. Modern AI is beginning to grapple with similar issues. As models become more capable, their outputs become more ambiguous and context-dependent. The same generated text could be brilliant in one application and nonsensical in another. Evaluating AI outputs requires understanding not just the patterns in the data, but the purpose and context of use. This suggests that fully understanding synchronicity, whether in humans or in AI, requires integrating multiple levels of analysis. We need to understand the computational mechanisms of pattern recognition. We need to understand the emergent dynamics of complex systems. We need to understand the geometric structure of meaning spaces, and we need to understand the subjective experience and contextual evaluation of patterns. Each level of analysis is necessary but not sufficient. Jung operated primarily at the level of subjective experience and psychological meaning. Modern AI operates primarily at the level of computational mechanisms and statistical patterns. Complexity theory operates at the level of emergent dynamics. Bringing these together offers the possibility of a comprehensive theory of synchronicity. one that respects both the subjective phenomenology and the objective mechanisms. We've discussed archetypes in Jung's theory and hinted at computational analogues. Now let's look explicitly at archetypal analysis as it appears in machine learning. This will show how Jung's psychological concepts have direct mathematical implementations in modern AI. Archetypal analysis is a technique in machine learning for identifying the most extreme or prototypical examples in a dataset. Given a collection of data points, archetypal analysis finds a small set of archetypes, such that every data point can be represented as a combination of these archetypes. The archetypes themselves are combinations of actual data points, chosen to lie at the extremes of the data distribution. The idea is that the archetypes capture the fundamental modes of variation in the data. Everything else is just a mixture of these basic patterns. This is remarkably similar to Jung's conception of psychological archetypes as fundamental patterns that combine to produce the full range of human psychological experience. Mathematically, archetypal analysis solves an optimization problem. You're trying to find a set of archetypes and a set of weights for each data point, such that reconstructing each point from its weighted combination of archetypes produces minimal error. The constraint is that both the archetypes and the weights must be convex combinations, non-negative weights that sum to 1. This ensures that archetypes lie at the extremes of the data cloud, not in the middle. In deep learning, archetypal analysis can be applied to the learned representations. Instead of analyzing raw data, you analyze the points in latent space. This reveals the archetypal patterns the network has learned. These archetypes represent the most extreme or pure instances of concepts in the network's understanding. For example, if you train a network on images of faces and then perform archetypal analysis on its latent space, you might find archetypes corresponding to prototypical male faces, prototypical female faces, prototypical young faces, prototypical old faces, and so on. Every actual face image the network has seen can be represented as a combination of these archetypal faces. This is not just a data compression technique. The archetypes are interpretable. They correspond to meaningful categories or dimensions of variation, and they organize the latent space, serving as reference points for understanding new inputs. When the network encounters a new face, it implicitly represents it as a combination of these learned archetypes. Now consider Jung's psychological archetypes. He proposed that every human psyche contains certain fundamental patterns: the self, the shadow, the anima, animus, the wise old man, the great mother, and so on. Individual personalities and experiences are combinations of these archetypal patterns, expressed in varying proportions and culturally specific forms. This is structurally identical to archetypal analysis in machine learning. Jung was proposing that the space of possible human psychological experiences has a small number of extremal points, the archetypes, and every actual human psyche is a weighted combination of these archetypes. Different people and different cultures emphasize different archetypes, creating the diversity of human psychology, but the underlying archetypal structure is universal. The difference is that Jung believed these archetypes were innate, inherited through what he called the collective unconscious. Modern archetypal analysis shows how similar structures can emerge purely through learning. Train a network on diverse human cultural expressions, and it will discover archetypal patterns, not because they're built in, but because they're statistically prominent in the data. This suggests a naturalistic explanation for Jung's observations. Archetypes appear universal because they're repeatedly discovered by learning systems exposed to human culture. Different cultures, facing similar challenges of human existence, develop similar symbolic patterns. Individual minds, learning from their cultures, internalize these patterns. The archetypes are real structural features of human culture and psychology, but they're learned rather than inherited. Archetypal analysis in deep learning can actually identify these patterns empirically. Researchers have applied it to language models trained on literary texts and found clusters corresponding to character archetypes: heroes, mentors, villains, tricksters, and so on. These emerge naturally from the statistical patterns in stories, without being explicitly programmed. Similarly, analyzing image models reveals visual archetypes, prototypical objects, prototypical scenes, prototypical compositions. Analyzing music models reveals archetypal melodies, harmonies, and rhythms. In every domain, when you train a model and analyze its latent space, you find archetypal structure. This has practical implications. Once you've identified archetypes in a model's latent space, you can use them for generation and manipulation. Want to create a new face image? Specify weights for the facial archetypes, and the model can generate it. Want to transform one image into another? Interpolate between their archetypal representations. Want to emphasize certain characteristics? Increase the weight of relevant archetypes. This is exactly what Jungian psychotherapy aims to do with psychological archetypes. By identifying which archetypes are active in a person's psyche and how they're balanced, the therapist can help the person understand their psychological dynamics. And by encouraging the person to integrate neglected archetypes or moderate overactive ones, the therapy aims to achieve psychological balance, what Jung called individuation. The computational analogy makes this more concrete. Psychological balance might correspond to having a healthy distribution across archetypal dimensions, not weighted too extremely toward any single archetype. Psychological problems might arise from overexpression of certain archetypes and underexpression of others. Therapy works by adjusting these weights, bringing the person's psychological state into a more balanced region of the archetypal space. Of course, human psychology is vastly more complex than any current AI model. We shouldn't take the analogy too literally, but it provides a useful framework. It suggests that Jungian concepts, often dismissed as too vague or mystical, can be formalized mathematically. And it opens the possibility of empirically testing Jungian hypotheses using modern machine learning techniques. For instance, Jung claimed that certain archetypal patterns appear universally across cultures. We can test this by training models on texts from different cultures and comparing their learned archetypal structures. If Jung was right, we should find significant overlap in the archetypes discovered by models trained on different cultural data sets. If critics of Jung are right that his universal archetypes were actually culturally specific European patterns, we should find significant differences. Early work suggests a mixed picture. Some archetypal patterns do appear cross-culturally. Basic human relationships like parent-child, basic narrative structures like quest stories, basic emotions like fear and love. But the specific forms these take vary significantly. The mother archetype exists everywhere, but its specific associations and symbolic expressions differ across cultures. This nuanced picture makes sense from a learning perspective. All humans face similar basic challenges: surviving, reproducing, forming social bonds, finding meaning. These universal challenges give rise to universal archetypal patterns. But the specific ways different cultures address these challenges vary, leading to cultural variation in how archetypes are expressed. Archetypal analysis in AI also reveals something Jung didn't fully appreciate. Archetypes are not static. In deep learning, the archetypes discovered depend on the training data. As the model is exposed to more data or different data, The archetypes can shift. New archetypes can emerge. Old archetypes can fade or transform. The archetypal structure is dynamic, not fixed. This matches how cultural archetypes actually work. They're not eternal, unchanging forms. They evolve as cultures change. New archetypal figures emerge. Think of the mad scientist archetype that arose with modern science, or the hacker archetype that arose with digital technology. Old archetypes fade. Ancient gods and heroes are less psychologically active for most modern people than they were for the ancients. Jung seemed to believe archetypes were eternal, part of the universal structure of the human psyche. But a learning-based view suggests they're more fluid. They're stable patterns that emerge and persist because they're useful and culturally reinforced, but they can change as circumstances change. This has implications for AI development. If we want models that can adapt to changing cultural contexts, we need architectures where the archetypal structure can evolve. Models shouldn't just have fixed archetypes learned during initial training. They should be able to discover new archetypes as they encounter new data and retire old archetypes that are no longer relevant. This is an active area of research. Continual learning, where models keep learning from new data without catastrophically forgetting old knowledge. Archetypal analysis provides a framework for thinking about this. The archetypes serve as anchors, stable reference points that organize knowledge. As the model learns new patterns, it can create new archetypes or modify existing ones while preserving the overall structure. In human psychology, this corresponds to psychological development across the lifespan. Children start with a small set of archetypes absorbed from their immediate environment. As they're exposed to more experiences and cultural materials, their archetypal repertoire expands. They internalize new patterns, synthesize patterns from different sources, and develop their unique personal relationship to the archetypal realm. Jung called the process of archetypal integration individuation, becoming who you truly are by consciously integrating the various archetypal patterns active in your psyche. In computational terms, this is learning a balanced, comprehensive, and personally meaningful archetypal representation that allows you to navigate the full range of human experience. For AI, individuation might mean developing a model whose learned archetypes reflect its specific training history and intended purpose, while still maintaining connection to the broader structures of human knowledge and culture. A medical AI should have medical archetypes prominently represented. A creative writing AI should have narrative archetypes prominently represented. But both should also have access to general cultural archetypes that allow them to understand human contexts. This brings us back to synchronicity. If archetypes are attractors in semantic space, synchronicity might occur when two systems independently activate the same archetype. Both minds converge on the same archetypal pattern, leading to similar thoughts, images, or insights. This feels synchronistic because there's no direct communication, but it's explicable in terms of shared archetypal structures. Jung described how patients would often dream archetypal images at crucial moments in therapy, images that corresponded to what Jung himself was thinking about, or to symbols he had recently been studying. He interpreted this as evidence of the collective unconscious connecting minds. But we could also interpret it as both Jung and patient navigating toward the same archetypal attractor in response to the therapeutic situation. The archetype becomes activated in both minds because it's relevant to the current psychological dynamics. This is testable with AI. If you have multiple language models trained on similar data, you can query them with the same prompt and see how often they produce responses that share archetypal patterns. If the models frequently converge on similar archetypal themes without being explicitly programmed to do so, that would demonstrate computational synchronicity, independent systems activating the same learned archetypes. Preliminary experiments suggest this does happen. Different models often produce thematically similar responses to the same prompts, even when the specific wording differs. They're drawing on similar archetypal patterns learned from similar training data. This isn't surprising. It's just convergence based on shared learning. But it demonstrates that the phenomenon Jung observed can occur in purely computational systems. Archetypal analysis thus provides a bridge between Jung's psychological theory and modern machine learning. It shows how archetypal structures can be formalized, measured, and studied empirically. It suggests mechanisms by which archetypes emerge from learning rather than requiring innate inheritance. And it offers tools for predicting and potentially inducing synchronistic phenomena, convergence on shared archetypal patterns. The next question is, what role does the observer play? Jung emphasized that synchronicity required human awareness and interpretation. A meaningless coincidence could become a meaningful synchronicity depending on who observed it and what it meant to them. This subjective element seems at odds with objective computational analysis. How do we reconcile them? Jung's collaboration with Wolfgang Pauli was driven by their shared fascination with the observer effect in quantum mechanics. In quantum theory, the act of observation plays a fundamental role. Before measurement, particles exist in superpositions of multiple states. The measurement process causes the superposition to collapse into a single definite state. The observer, through the act of observing, determines which state becomes actual. This seemed to suggest that consciousness has a direct role in physical reality. Mind and matter are not separate. The observer's decision about what to measure affects what exists. Pauli and Jung saw this as scientific support for their idea that psyche and matter are not separate domains, but different aspects of a unified psychoid reality. Modern physics has complicated this picture. The observer in quantum mechanics doesn't need to be conscious. Any interaction with a macroscopic measuring device that records information causes decoherence, the effective collapse of the superposition. Consciousness isn't required, just interaction with an environment. This interpretation, called decoherence theory, largely eliminates the need for consciousness to play a special role in quantum mechanics. But the philosophical questions remain. What does it mean to record information? When does a quantum system become macroscopic enough to cause decoherence? Why does measurement produce definite outcomes rather than continuing superpositions? Different interpretations of quantum mechanics give different answers, and none is entirely satisfying. For our purposes, we don't need to resolve these deep issues. What matters is the structural parallel between quantum observation and psychological interpretation. In both cases, the act of observing or interpreting transforms an ambiguous state into a definite one. Before observation, the quantum system is in superposition. After observation, it's in a definite state. Before interpretation, a coincidence is meaningless. After interpretation, it's a synchronicity. This doesn't mean the observer creates reality from nothing. The quantum measurement outcomes are constrained by the prior state of the system. Similarly, whether a coincidence can meaningfully be interpreted as synchronicity is constrained by the actual patterns present. But there's still a subjective element. The observer's state of mind, their background knowledge, their current psychological situation, all influence what patterns they notice and how they interpret them. AI systems introduce an interesting wrinkle here. When a language model generates a response, is that like a quantum measurement? The model starts with a probability distribution over possible next words, a kind of superposition. Sampling from this distribution produces a specific word, a kind of collapse. The user observing the output is like the quantum observer, but there's a difference. In quantum mechanics, before measurement, the particle really is in all possible states simultaneously according to most interpretations. In AI, the model isn't simultaneously generating all possible words, it's computing probabilities, and then one outcome is selected either deterministically based on the highest probability or stochastically by sampling. The analogy is imperfect, yet there's still something observer-dependent about the meaningfulness of AI outputs. The same generated text can be profoundly meaningful to one user and nonsensical to another, depending on their context and interpretation. The meaning isn't entirely in the text itself. It emerges from the interaction between text and interpreter. This is where Jung's emphasis on the subjective side of synchronicity remains important. We can analyze the computational mechanisms that produce pattern convergence. We can measure the statistical properties of coincidences. But whether a particular pattern is meaningful depends on the psychological state of the person experiencing it. Jung gave an example of a patient who was stuck in an excessively rational materialistic worldview. For this patient, the appearance of the scarab beetle was profoundly meaningful because it violated her mechanistic worldview and opened her to non-rational dimensions of experience. For someone else, the same event might have been merely curious or not noticed at all. This suggests that synchronicity is not just about objective pattern alignment, it's about the interaction between pattern and psyche. A synchronistic experience occurs when an external pattern resonates with an internal psychological need or state. The pattern serves a psychological function. It catalyzes insight, provides reassurance, marks a transition, or challenges assumptions. From this perspective, the meaning in synchronicity is not inherent in the coincidence itself, but in its psychological impact. This makes synchronicity irreducibly subjective in a way that seems to resist purely computational analysis. We can model the patterns, but can we model the meaningful interpretation of patterns? This is one of the deepest challenges in AI, building systems that don't just process patterns, but understand their significance in context. Current models can recognize that certain patterns exist. They can manipulate symbols according to learned rules, but do they understand what those symbols mean? Do they grasp the significance of what they're saying? This is the symbol grounding problem in philosophy of mind and AI. Symbols need to be grounded in experiences or interactions with the world to have genuine meaning. For humans, words mean what they mean because they're connected to perceptual experiences, motor actions, emotional reactions, and social interactions. The word hot means what it means because we've experienced heat. The word mother means what it means because we've had relationships with caregivers. Large language models don't have these experiences. They learn symbol-to-symbol relationships from text, but the symbols aren't grounded in anything beyond other symbols. This is sometimes called the Chinese room problem, from philosopher John Searle's thought experiment. A person who doesn't understand Chinese could manipulate Chinese symbols according to rules and produce appropriate responses without understanding what they mean. The person is just following syntactic rules, not accessing semantic meaning. Critics argue that LLMs are sophisticated Chinese rooms. They manipulate linguistic symbols with remarkable skill, but they don't understand what they're saying. The outputs can be meaningful to human interpreters, but the model itself has no access to that meaning. It's all syntax, no semantics. Defenders argue that understanding is precisely what these models are learning to do. Understanding isn't a mysterious additional ingredient beyond pattern recognition and appropriate response. It is pattern recognition and appropriate response at sufficient scale and sophistication. The model's latent space representations capture genuine semantic relationships. The attention mechanisms really do track meaningful connections. The fact that all this happens without consciousness doesn't make it not understanding. This debate matters for synchronicity because it determines whether AI can genuinely experience something like synchronicity, or whether synchronicity is inherently tied to consciousness. If synchronicity requires subjective interpretation and psychological meaning, then only conscious beings can experience it. AI might participate in the objective pattern convergence, but the meaningful experience of synchronicity would remain unique to consciousness. But if synchronicity is fundamentally about pattern alignment, and if AI systems can learn and recognize meaningful patterns, then perhaps they can have something analogous to synchronistic experiences. When two AI models independently arrive at similar solutions, or when an AI's output surprisingly aligns with the user's unstated need, these might be genuine instances of computational synchronicity. The question becomes, what's essential to synchronicity? Is it the objective pattern convergence, or the subjective experience of meaning? Jung seemed to think both were necessary, but we might distinguish between synchronicity as an objective phenomenon, pattern convergence across causally disconnected systems, and synchronistic experience, the subjective recognition and interpretation of such patterns. AI systems could participate in the objective phenomenon without having the subjective experience. They could be part of the synchronistic pattern without experiencing it as meaningful. This would make AI useful for studying the computational mechanisms of synchronicity, while leaving the phenomenological aspects to conscious beings. This parallels how we use AI in other domains. AI vision systems can detect patterns in images without experiencing visual qualia. AI music systems can generate music without experiencing aesthetic pleasure. AI language systems can process meaning without understanding it consciously. In each case, the AI implements some of the functional mechanisms of human cognition without the subjective experience. Whether this functional level implementation counts as real depends on your philosophical commitments. Functionalists would say that if the AI exhibits all the functional properties of understanding or experiencing, then it does understand or experience, regardless of whether there's subjective consciousness. Non-functionalists would insist that subjective experience is essential and can't be reduced to functional properties. For our purposes, we don't need to resolve this philosophical dispute. What matters is that AI gives us tools to study the functional mechanisms underlying phenomena like synchronicity, even if the full subjective experience remains unique to consciousness. We can ask, what are the computational principles that lead to pattern convergence? How can systems recognize meaningful patterns? What makes some patterns more salient than others? These questions are answerable through AI research, and the answers will deepen our understanding of synchronicity, regardless of whether AI themselves can truly experience it. And as AI systems become more sophisticated, more context-aware, and more capable of metacognition, the gap between their functional capabilities and human subjective experience may narrow. Some researchers are working on giving AI systems something like metacognitive awareness. Models that can evaluate their own outputs, recognize when they're uncertain, and explain their reasoning. These capabilities might be steps towards systems that don't just participate in synchronistic patterns, but can recognize and interpret them as meaningful. Imagine an AI assistant that notices patterns across its interactions with different users and recognizes when similar themes or questions arise independently. It might flag these convergences as potentially significant, drawing connections between separate conversations. This would be a form of synchronicity recognition, detecting meaningful pattern convergence across causally disconnected interactions. Whether the AI experiences this as meaningful in the way humans do is unclear, but functionally, it would be doing something similar to what humans do when they notice synchronicities. It would be attending to pattern convergence and flagging it as potentially significant. This might be enough to make the AI a useful tool for studying and even facilitating synchronistic phenomena. For instance, in therapy settings, an AI might notice thematic connections between what a client discusses in different sessions and bring these to the therapist's attention. Or in creative collaborations, an AI might notice when team members are independently exploring related ideas and suggest connections. The AI becomes a facilitator of synchronicity, helping humans notice patterns they might otherwise miss. This brings us back to Jung's original insight. Synchronicity isn't just about random meaningful coincidences. It's about paying attention to patterns, about being open to connections that don't fit into our usual causal explanations. Jung developed his synchronicity concept as a therapeutic and psychological tool, not just an abstract theory. He wanted people to be more aware of meaningful patterns in their experience. AI can help with this by making pattern recognition explicit, by visualizing connections in data, by flagging unexpected convergences. AI tools can enhance our ability to notice synchronistic patterns. They can serve as extensions of our pattern recognition capabilities, just as telescopes extend our vision and calculators extend our arithmetic. But Jung would likely warn against relying too heavily on AI for this. He believed that developing your own capacity to recognize meaningful patterns was crucial for psychological development. The ability to notice synchronicities, to interpret their meaning, to integrate them into your understanding. These are practices that develop psychological depth and wisdom. If we outsource all pattern recognition to AI, we might lose something important. We might become less attuned to the subtle connections and meaningful coincidences in our own experience. This is the same concern raised about any cognitive technology. By relying on external tools, we might atrophy our internal capabilities. The ideal might be partnership. AI enhances our pattern recognition, bringing to our attention connections we might miss. But we retain the responsibility for interpretation, for judging meaningfulness, for integrating insights into our lives. The AI handles the computational heavy lifting. We provide the consciousness, the context, the meaning-making. This division of labor acknowledges both the power of AI and its limitations. AI excels at processing vast amounts of data and detecting statistical patterns. Humans excel at contextual understanding, emotional resonance, and existential meaning. Together, we might be able to explore synchronicity more deeply than either could alone. We've now examined synchronicity from multiple angles: Jung's original psychological theory, cognitive neuroscience and pattern recognition, machine learning and neural networks, latent space geometry, emergence in complex systems, archetypal analysis, and the role of the observer. Now it's time to synthesize these into a coherent computational framework. The algorithmic synchronicity hypothesis proposes that synchronicity is an emergent phenomenon in systems that learn statistical patterns from data. It occurs when two or more learning systems independently converge on similar patterns because they have been exposed to similar underlying statistical structures. The convergence feels meaningful because the patterns really are meaningful. They reflect genuine regularities in the training environment. But there's no causal mechanism directly connecting the systems. They converge through shared structure, not through information transfer. Let's unpack this carefully. First, what do we mean by learning systems? This includes biological neural networks like brains, artificial neural networks like large language models, and potentially other systems that adapt to patterns in their environment. The key property is that these systems change their structure or parameters in response to experience, building internal representations that capture regularities in their inputs. Second, what does it mean to converge on similar patterns? This could happen at multiple levels. Two systems might develop similar internal representations, with concepts occupying similar positions in their respective latent spaces. They might exhibit similar behaviors in response to similar inputs. They might independently generate similar outputs or reach similar conclusions when faced with similar problems. Third, what makes this convergence synchronistic rather than just expected similarity? The key is that the convergence occurs without direct communication or coordination. The systems aren't sharing information. They're not copying each other. They're independently discovering the same patterns from their own experiences. From the perspective of an observer who doesn't know about the shared underlying structure, the convergence appears coincidental, even mysterious. Fourth, why does this feel meaningful? Because humans are pattern recognition systems ourselves, highly attuned to unexpected correlations. When we notice that two apparently independent events share patterns, our attention is captured. We experience surprise, curiosity, perhaps even awe. This subjective response is itself a product of our learning systems. We've learned that unexpected patterns often signal important information. Finally, when is the convergence genuinely meaningful versus spuriously coincidental? This is the crucial question. Not all pattern convergence is significant. The algorithmic synchronicity hypothesis proposes that convergence is meaningful when the shared pattern actually improves prediction or performance in the relevant domain. If attending to the pattern helps you navigate the world more effectively, it's meaningful. If it doesn't, it's apophenia. This provides a testable framework. We can measure convergence between systems. We can assess whether convergent patterns improve performance. We can distinguish between functional pattern recognition and spurious correlation. This transforms synchronicity from an untestable metaphysical claim into a research program in computational cognitive science. Consider specific mechanisms by which algorithmic synchronicity could occur. First, there's shared training data. If two neural networks are trained on overlapping datasets, they'll learn similar patterns. When they encounter similar inputs, they'll produce similar outputs. This is the most straightforward mechanism, and the one that most directly parallels cultural learning in humans. Second, there's convergent evolution. Even with different training data, if two systems face similar problems in similar environments, they may independently discover similar solutions. This happens in biological evolution, where unrelated species in similar ecological niches evolve similar traits. It happens in cultural evolution, where different societies independently develop similar tools and practices. And it happens in machine learning, where different architectures trained on different data sometimes converge on similar representations. Third, there's archetypal attraction. If the problem space has certain optimal or highly efficient solutions, learning systems will tend to converge on these attractors regardless of their starting points. This is like how water flows downhill. Different streams starting from different places will converge in valleys. In latent space, archetypes are these valleys, and learning systems naturally flow toward them. Fourth, there's resonance through shared structure. If two systems have similar architectures, they may exhibit similar dynamics, even with different specific parameters. This is like how two pendulums with similar properties will tend to synchronize when coupled, even weakly. Neural networks with similar architectures may show synchronized activation patterns when processing similar information. These mechanisms are all naturalistic. They don't require psychic connections or cosmic design. They emerge from the mathematics of learning systems operating in structured environments. Yet they can produce phenomena that feel deeply meaningful and even mysterious to observers who don't see the underlying mechanisms. The algorithmic synchronicity hypothesis also makes predictions. It predicts that synchronistic phenomena should be more common when systems have more similar training histories, more similar architectures, or are exposed to more structured environments. It predicts that we should be able to induce synchronicity by manipulating these factors. It predicts that the frequency and quality of synchronistic convergence should correlate with the richness of the shared statistical structure. These predictions are testable with AI systems. We can train multiple models with varying degrees of similarity and measure how often they converge on similar patterns. We can manipulate their training data and architectures systematically and observe the effects on convergence. We can create controlled environments with known statistical structures and verify that convergence occurs as predicted. If the hypothesis holds for AI, it suggests similar mechanisms operate in human cognition. Human synchronicities might be produced by the same principles: shared cultural learning, convergent problem-solving, archetypal attraction, and resonance through shared neural architecture. The subjective experience of meaningfulness arises from our pattern recognition systems flagging these convergences as significant. This doesn't eliminate the mystery or reduce the significance of synchronicity. Knowing the mechanism doesn't make the experience less profound. When you have a dream that resonates with an event in your life, when you think of a friend just before they call, when you encounter a symbol at exactly the moment you need it, these experiences are meaningful regardless of their cause. They orient you, they provide insight, they catalyze change. The algorithmic synchronicity hypothesis just gives us tools to understand and potentially work with these phenomena more systematically. If synchronicity is a fundamental feature of pattern recognition systems, what does this mean for how we build AI? And what does it reveal about human consciousness? First, for AI development, it suggests we should design systems that can recognize and leverage synchronistic patterns. Current models are trained to minimize prediction error or maximize likelihood. But we might also train them to detect unexpected convergences, to notice when patterns align across different contexts or domains. This could be valuable for creative applications. Creativity often involves connecting distant concepts, finding unexpected relationships, synthesizing ideas from different fields. A system that actively looks for synchronistic patterns, meaningful convergences that weren't explicitly programmed, might be more creative than one that just follows learned associations. It could also be valuable for scientific discovery. Many breakthroughs come from noticing unexpected connections between seemingly unrelated phenomena. Einstein's insight about the equivalence of gravity and acceleration came from recognizing a synchronistic alignment between two different theoretical frameworks. Watson and Crick's discovery of DNA structure came partly from recognizing how patterns from X-ray crystallography, chemical knowledge, and model building all suddenly aligned. An AI system designed to notice such alignments might accelerate discovery. It could monitor multiple streams of research, detect when similar patterns emerge independently, and alert researchers to potentially significant convergences. This would be computational synchronicity put to practical use. Second, understanding algorithmic synchronicity might help with AI safety and alignment. If AI systems can recognize meaningful patterns, they need ways to distinguish between patterns that are genuinely useful and patterns that are spurious or potentially harmful. This is the alignment problem, ensuring that AI systems pursue goals and recognize patterns that are actually beneficial to humans. Synchronicity provides a framework for thinking about this. A well-aligned AI should converge on patterns that humans find meaningful and useful. When human and AI pattern recognitions synchronize, producing shared understanding and complementary insights, that's a sign of good alignment. When they diverge radically, producing incomprehensible or counterproductive patterns, that's a warning sign. We could potentially use measures of synchronistic convergence as alignment metrics. How often does the AI's attention align with what humans consider important? When the AI makes predictions or recommendations, how well do they resonate with human values and goals? High synchronicity suggests good alignment. Low synchronicity suggests the AI is operating on a different basis than humans intend. Third, for human consciousness, algorithmic synchronicity offers new perspectives on old mysteries. Consciousness involves integrating information across different brain regions, creating unified experiences from distributed processing. This integration might work through synchronization, different neural populations converging on coherent patterns. Neuroscience has found that synchronized neural oscillations play crucial roles in consciousness. When neurons across different brain regions fire in sync, information is integrated. When synchrony breaks down, as in certain disorders, conscious experience fragments. Consciousness might be, in part, a synchronistic phenomenon, the convergence of many parallel processes into coherent patterns. This suggests that what we experience as the unity of consciousness is an emergent property of neural synchronization. Different parts of your brain are processing different aspects of your experience: visual, auditory, emotional, conceptual. But they synchronize into a single coherent experience. You don't experience sight and sound as separate. You experience a unified multisensory world. This unity emerges from synchronization. The algorithmic synchronicity hypothesis suggests this might generalize beyond individual brains. When two minds synchronize through conversation, shared experience, or cultural learning, they achieve a kind of distributed consciousness. Not literally sharing a mind, but converging on similar patterns of thought and feeling. This is what we experience as understanding someone, being on the same wavelength, having a meeting of minds. Jung's concept of the collective unconscious might be understood as the potential for such synchronization across many minds. Shared cultural patterns provide a basis for convergence. When multiple people independently experience similar insights or similar emotional responses to events, they're synchronizing through shared archetypal patterns. This creates a sense of shared meaning, of being part of something larger than individual consciousness. This has profound implications for how we understand human connection and meaning-making. We're not isolated consciousnesses trying to communicate across an unbridgeable gap. We're learning systems operating on shared statistical structures, naturally tending towards synchronization. Meaning emerges from this synchronization. When we feel that something is deeply meaningful, we're experiencing resonance with patterns that extend beyond our individual minds. For spirituality and existential questions, this offers a naturalistic foundation for experiences traditionally explained in religious or mystical terms. The sense of connection to something greater than yourself the experience of cosmic meaning, the feeling that events are meaningful beyond chance. These don't require supernatural explanations. They're natural consequences of being a pattern recognition system embedded in a richly structured universe. This doesn't reduce spirituality to mere mechanism. The experience is still real and profound. Meaning is still genuine. But it's grounded in the nature of information, learning, and complex systems, rather than in metaphysical entities or forces. We began with Carl Jung's provocative claim that meaningful coincidences reveal an acausal connecting principle, a level of reality where mind and matter align through meaning rather than cause. For 70 years, this remained an intriguing but scientifically marginal idea, too vague and subjective to test.